In the northwest corner of Wyoming, beneath a geyser that erupts almost on schedule every 90 minutes, there is a chamber of molten rock. It sits 8 kilometers below the surface, about the cruising altitude of a passenger jet, but in the other direction, downward, into the crust of the Earth. The chamber holds 10,400 cubic kilometers of rhyolitic magma. To put that in a shape your mind can hold, imagine the Grand Canyon filled to the rim with molten stone, then imagine doing it 2.5 times over. The chamber is roughly 30 kilometers wide and 90 kilometers long, with a temperature near 800 degrees Celsius. It is not, despite what films suggest, a great glowing lake. It is more like a sponge made of hot rock, mostly solid, with pockets of liquid magma trapped in the spaces between crystals. And every single day, 3 million people walk on the ground above it, take photographs, eat sandwiches at the visitor center, and look at the geyser they came to see. They are standing on the lid of the largest active magma reservoir in North America. Most of them have no idea. The geyser is called Old Faithful. The chamber underneath it has no name. It does not need one. It is simply the thing that is there, the thing that has been there, in one form or another, for the last 16 million years. Yellowstone is not really a volcano in the way most people imagine a volcano. There is no cone, no crater rim you can stand on the edge of, no dramatic peak. The whole national park, all of its meadows and rivers and forests of lodgepole pine, sits inside the volcano. The crater is 55 kilometers wide and 80 kilometers long, and you only notice it from the air or on a map, or when you understand what you are looking at. From the ground, it looks like a beautiful place where bison graze and the rivers run clear. But the rivers are warmer than they should be. The ground in some places is too hot to walk on. The trees in certain meadows die in patches, killed by carbon dioxide rising silently through the soil. Yellowstone exhales about 45,000 tons of carbon dioxide every single day, and that gas comes from the magma below, molecules of ancient breath leaking up through the rock. The geysers and hot springs and bubbling mud pots are not random scenery. They are the surface expression of something that lives underneath. The planet, in this one corner of Wyoming, breathes. The most famous of those features is Old Faithful, but there is also Grand Prismatic Spring, which is the size of a football field and coloured in concentric rings of orange and yellow and deep cobalt blue, the colours made by heat-loving bacteria that thrive at temperatures which would kill almost anything else. There is Mammoth Hot Springs, where mineral-rich water has built terraces of travertine that look like a frozen waterfall made of bone-white stone. There are mud pots that boil and gurgle and smell of sulphur, and fumaroles that hiss steam into the cold mountain air. All of this exists because of what is happening 8 kilometers down. And here is where the story turns strange, because Yellowstone is not actually a volcano in the geological sense. It is something rarer, and in many ways more interesting. It is a hotspot, a fixed plume of hot rock rising from somewhere very deep, holding its position while the entire continent slides slowly over the top of it. The North American plate moves westward at about 2 centimeters per year, which is roughly the rate at which your fingernails grow. The hotspot does not move. It just sits there, melting through the crust above it, leaving a trail. That trail is visible if you know where to look. It runs across southern Idaho for 700 kilometers, a curving valley called the Snake River Plain. And along that valley you can find the buried remains of older calderas, the corpses of ancient Yellowstones, each one formed when the hotspot sat beneath a different patch of ground. 16 million years ago, the hotspot was under what is now eastern Oregon. Then it was under southern Idaho, then central Idaho. Now it is under Wyoming. In another few million years, it will be somewhere in Montana, and there will be a new Yellowstone, and the old one will be a quiet valley that nobody visits. So when you stand at Old Faithful and look down at the wooden boardwalk under your feet, you are not just standing above a volcano. You are standing above the current address of something much older, something that has been moving very slowly across the western United States since before our species existed. And the chamber beneath your feet has done what chambers like this do. It has erupted before. It has erupted 3 times, in fact, in the last 2 million years. Each time, it changed the climate of the entire planet. Yellowstone has erupted 3 times. 3 times the ground has split open and the sky has gone dark with ash. 3 times the western half of North America has been buried under meters of glassy stone. 3 times the world has cooled. The harvests have failed somewhere. The ecosystems have collapsed and rearranged themselves. And 3 times, this is the part that matters, the planet has come back. Not the same. Different species, different forests, different patterns of weather. But it came back. It always comes back. That is the thing to hold on to as we go through this. The story of Yellowstone is not really a story about disaster. It is a story about something the planet does regularly over geological time and how it keeps doing it without ending. The Earth has survived itself many times. It will survive itself many more. We are very small inside that fact, and it is, in its own quiet way, a comforting thing to know. Before we go any further, I want to mention one thing. If this is the kind of story you find yourself coming back to, the slow, deep ones, the ones about how the planet actually works, then subscribing to the channel helps more than you might think. It tells the algorithm to keep finding people like you. And in the comments, I would love to know where you are listening from tonight. What city, what time of day, how far you are from Yellowstone in kilometers or miles. I read them. It makes the whole thing feel less like broadcasting and more like a conversation across the dark. Now, the chamber under Old Faithful, the 10,000 cubic kilometers of magma. The question we have not yet asked, the one that everything else depends on, is how it got there in the first place. Because the answer is not in Wyoming. The answer is not even in the crust. The answer begins 3,000 kilometers down, at the boundary between the Earth's mantle and its molten iron core, where the temperature is over 4,000 degrees and the pressure is so great that solid rock behaves like the slowest possible liquid. That is where the story actually starts. So let us go down there, all the way down. 3,000 kilometers below the surface of the Earth, at the boundary where the rocky mantle meets the molten iron core, the temperature is somewhere around 4,000 degrees Celsius. That is hot enough to vaporize almost anything you can think of. But down there nothing vaporizes because the pressure is so enormous that matter does not behave the way it does up here. Solid rock, under that kind of pressure, flows, slowly, over millions of years, like a glacier made of stone, except the stone is hot enough to glow if you could somehow see it, which you cannot, because no light has ever reached that depth, and no light ever will. This boundary, the place where mantle meets core, is the deepest interface in our planet. And it is not flat, it is not smooth. The core is hotter than the mantle, much hotter, and that difference in temperature is fundamentally unstable. Heat wants to move from hot places to cold places. It is one of the few things in physics you can absolutely count on. So heat does what heat always does. It rises. The way it rises matters, because it does not rise as a uniform sheet. The mantle above the core is too thick and too viscous for that. Instead, in certain places, for reasons that have to do with the shape of the core and the chemistry of the rock and 100 other factors we still do not fully understand, the heat collects. It pools. It forms a column. And once a column starts to form, it tends to keep forming, because the hot rock at its center is slightly less dense than the cold rock around it, and less dense things rise, the way a bubble of warm air rises through cold air on a summer afternoon. Except this bubble is made of rock, and it is 350 kilometers wide, and it takes tens of millions of years to make the journey from the core to the surface. Geologists call this kind of structure a mantle plume, and the one we are concerned with, the one that has been sitting under various parts of the western United States for the last 16 million years, was finally imaged in detail in 2018. A team led by a researcher named Peter Nelson, working with seismic data from a continent-wide array of sensors called US Array, traced the plume's outline using something called core phase tomography. The principle is simple, even if the math is not. When a large earthquake happens somewhere on the planet, the seismic waves it produces travel through the entire Earth, including down through the core and back up through the mantle on the other side. Hot rock slows those waves down. Cold rock lets them through faster. So if you have enough sensors and enough earthquakes, and you do the calculations carefully, you can essentially take an X-ray of the planet's interior. What Nelson and his team saw was unmistakable. A narrow, slightly tilted column of slow-moving rock, 350 kilometers across, rising all the way from the core mantle boundary to a point just beneath the crust under Wyoming. It is the deepest, clearest image we have ever made of a feature like this. The plume is not a tube of liquid lava. That image, which appears in so many bad documentaries, is wrong in almost every way that matters. The plume is solid rock, just hot enough and slightly less dense than its surroundings, rising at a rate of perhaps a few centimeters per year. If you could somehow stand inside it, you would not know you were inside anything at all. It would just feel like rock, like the rock everywhere else around it. Only by measuring its temperature very carefully or watching how seismic waves moved through it would you find any difference. The plume is 50 to 120 degrees hotter than the rock around it, which sounds like a lot in terms of weather but is almost nothing in terms of geology, where we are talking about temperatures already in the thousands. And yet that small temperature difference is enough. It is enough to make the rock rise. It is enough, when the plume reaches the upper mantle, to start melting things. Because somewhere around 400 kilometers down, the conditions become just right for the rock to begin transitioning from solid to partial melt, not because the temperature is increasing, but because the pressure is decreasing as you move upward, and rock that was perfectly happy being solid at high pressure will start to liquefy at lower pressure, even if you keep the temperature the same. This process is called decompression melting, and it is the engine that drives every hotspot volcano on Earth. The plume does not bring molten rock up from the core. It brings hot rock up, and the act of rising is what makes the rock melt. By the time the plume reaches the base of the lithosphere, the cold, brittle outer shell of the planet, at about 80 kilometers depth, it has spread out. The narrow column flattens against the underside of the crust like a mushroom cap, the way smoke flattens against a ceiling. And from that flattened layer, blobs and fingers of molten basalt push upward into the crust above, melting and reshaping the rock as they go. This is the process that built the chamber underneath Old Faithful. Not a single dramatic intrusion, but millions of years of slow, persistent heating from below, like a candle held under a sheet of plastic until the plastic begins to soften and sag. There is one detail about this whole arrangement that takes most people a moment to absorb, and it is worth slowing down for. The plume is essentially fixed in place. It is anchored to the deep mantle, 3,000 kilometers down, and it does not move very much over geological time. But the surface of the Earth, the crust, the continents, everything we live on, is not fixed. The North American plate is moving westward at about 2 centimeters per year, slow enough that you cannot feel it, but fast enough that, over millions of years, it adds up to something significant. The plume stays put. The continent slides over the top of it, and as it slides, the plume burns through whatever piece of continent happens to be sitting above it at the time, like a blowtorch held under a slowly moving sheet of metal. This is why hotspots leave tracks. If you look at a map of the western United States, you can trace the path the North American plate has taken over the Yellowstone hotspot for the last 16 million years. It runs from southeastern Oregon, where you find the buried McDermott caldera, the oldest volcanic center associated with this hotspot. From there, it cuts across southern Idaho along a long, curving valley called the Snake River Plain, which is essentially the scar left behind by the hotspot as it burned its way across the continent. Each piece of that valley was, at one time, a Yellowstone. Each one had its own magma chamber, its own caldera, its own history of eruptions. And then the plate moved on, the heat moved away, and the chamber cooled and the caldera filled in with sediment, and what was once a region of violent volcanism became a quiet agricultural valley where farmers grow potatoes and the wind blows through the wheat. Yellowstone, the Yellowstone of today, sits at the leading edge of that track. It is the youngest expression of the hotspot, and in another few million years, the same process will move it on. The North American plate will keep sliding southwest. The hotspot will stay put, and the heat that currently sits under Wyoming will end up under Montana, and then somewhere further northeast, and a new caldera will form there. And the place we call Yellowstone today will become quiet, the way the older calderas in Idaho are quiet, the way McDermott is quiet. The hotspot moves on. The continent forgets. That is the rhythm of it. But we are not interested in the future of Yellowstone, not yet. We are interested in the present. And in the present, the plume is still there, still rising, still pushing heat into the crust above it. The flattened cap of plume material under the lithosphere is feeding magma into the rocks above, and those rocks have been melting and remelting for millions of years, and the result of all that melting is something quite specific. It is a layered system, a kind of plumbing, that runs from the top of the plume all the way to the surface. There is a deep chamber, and above it a shallower chamber, and above that the hot springs and geysers and mud pots that are the things you actually see when you visit the park. And until very recently, we did not understand how any of it fit together. We had pieces, we did not have the picture. That changed in 2015, when a small team of seismologists in Salt Lake City spent several years combining two different kinds of earthquake data and discovered something that nobody had been able to see before. They found a second magma reservoir, a deeper one, a much, much larger one. And once they could see it, a great many things about Yellowstone, including the question of where all the carbon dioxide was coming from, finally started to make sense. For decades, there was a number that did not add up. Yellowstone exhales carbon dioxide. It does this constantly, day and night, summer and winter, through the soil and the hot springs and the fumaroles, releasing about 45,000 tons of the gas into the atmosphere every single day. The carbon comes from the magma. It has to, because the isotope signatures match, because the chemistry tells you so, because there is no other reasonable source for that much CO2 in that particular place. So the carbon comes from the magma. That part was never in question. The question was simpler and much more troubling. There was not enough magma to account for it. The shallow chamber that geologists had mapped under the caldera, the one we were just talking about, the 10,000 cubic kilometers of partially molten rock sitting between 5 and 17 kilometers below the surface, that chamber, big as it is, simply does not contain enough material to produce the volume of carbon dioxide that Yellowstone is putting out. It is like trying to explain the smoke from a forest fire when all you can see is a single burning log. You know there must be more burning somewhere. You just cannot see it. For years, geologists assumed the rest of the carbon must be coming from somewhere deeper, from the plume itself, perhaps, or from some intermediate body of magma that was hidden between the plume and the shallow chamber, somewhere in the lower crust. The problem was that nobody could find it. The seismic instruments at the time were not sensitive enough to image structures at that depth with any clarity. So the deeper reservoir, if it existed, remained a hypothesis. A reasonable hypothesis, an inevitable hypothesis, given the chemistry, but not a confirmed one. And in science, the difference between reasonable and confirmed is the difference between everything. This is where a researcher named Xin-Hua Huang comes into the story, working at the University of Utah in Salt Lake City, alongside Fan-Chi Lin and Robert Smith and Jamie Farrell and a few collaborators at other institutions. Huang had been thinking about a problem that was, on the surface, technical and almost boring. Different kinds of seismic instruments produce different kinds of data, and those data sets are usually analyzed separately. The local network of seismometers around Yellowstone, run by the University of Utah, was very good at imaging shallow structures, the first 10 or 20 kilometers of crust, in fine detail. The continent-wide US array network was good at imaging deep structures, hundreds of kilometers down. But there was a gap in the middle, from about 20 to 50 kilometers depth, where neither system worked well on its own. And the deeper reservoir, if it existed, was almost certainly somewhere in that gap. Huang spent several years developing a method that combined both data sets, using each to fill in the weaknesses of the other. The math is involved, but the principle is intuitive enough. If you have two cameras, each one good at a different range of focus, and you can teach them to share information, you can build a single image that is in focus at every depth. That is essentially what Huang did. He taught the local data and the continental data to talk to each other. And in 2015, when he and his colleagues finally ran the calculation on the assembled Yellowstone dataset and looked at what came out, they saw something nobody had seen before. There was a second magma reservoir. It sat between 20 and 50 kilometers below the surface, exactly in the depth range that had been invisible to all previous studies. It was 46,000 cubic kilometers in volume, about 4.5 times the size of the shallow chamber that everyone had known about for decades. It was not made of the same kind of magma as the chamber above it. The shallow chamber holds rhyolite, a kind of magma that is rich in silica and viscous and gas-charged, the explosive kind. The deeper reservoir holds basalt, a much hotter, denser, runnier kind of magma that comes more or less directly from the mantle. The basaltic reservoir was the missing link between the plume below and the rhyolitic chamber above, the place where heat from the plume was being slowly transferred upward into the crust over millions of years. It was the reason the shallow chamber existed at all, and it was the source of the missing carbon dioxide. When the paper was published in the journal Science in April of that year, the discovery made headlines around the world, and most of those headlines got the story wrong. They reported that Yellowstone had grown larger, that the threat had increased, that the supervolcano was now even more dangerous than we had thought. None of that was true. The reservoir had been there all along. We had just finally learned to see it. As Robert Smith, one of the senior authors on the paper, told reporters at the time, the actual hazard had not changed. We had simply, after years of suspicion, found the thing we were looking for. But the discovery did matter, and it mattered in ways that were more interesting than the news coverage suggested. Because once you can see the entire system, plume, deep reservoir, shallow chamber, surface, you start to understand how the whole thing actually works. And the picture that emerges is very different from the one most people carry in their heads. Most people, when they think about a magma chamber, imagine something like a cavern full of glowing orange liquid, the way it appears in disaster films and on the covers of paperback novels. A pool of lava, walls of black rock, maybe a single dramatic stalactite hanging from the ceiling. None of this is correct. A real magma chamber, including both of the chambers under Yellowstone, looks nothing like that. It is mostly solid rock. The shallow chamber is somewhere between 5 and 15% molten, which means that at any given moment, 85 to 95% of the material in the chamber is solid crystal. The melt exists as droplets and pockets and thin films coating the surfaces of those crystals, like water held in the spaces of a wet sponge. The deeper reservoir is even less melted, only about 2%. It is essentially a vast region of very hot rock, with a small fraction of liquid distributed through it. This matters enormously, because the percentage of melt is the thing that determines whether a magma chamber can erupt. To produce a major eruption, the melt fraction needs to be much higher. The standard estimate is that you need at least 50% melt before the magma can mobilize and rise toward the surface in any significant volume. At 5 to 15%, the system is essentially locked. The crystals are touching each other, supporting each other, holding the structure rigid. You can heat it, you can stress it, you can subject it to small earthquakes, and nothing much happens. The chamber just sits there, hot and mostly solid, the way it has been sitting for tens of thousands of years. Which raises a question that every visitor to Yellowstone eventually asks, and which the US Geological Survey has had to answer thousands of times. Is there enough magma down there to actually produce another supereruption? And the honest answer, the answer the scientists at Yellowstone Volcano Observatory will give you when you ask them directly, is that we are not sure. The shallow chamber, in its current state, probably does not contain enough mobilized melt to feed the kind of catastrophic event that built the modern caldera 600,000 years ago. The system would need to change. The melt fraction would need to climb. New magma would need to be injected from below, slowly, over thousands or tens of thousands of years, until the conditions for an eruption were met. And we see no evidence that any such injection is currently happening. The chamber is, if anything, slowly cooling. The caldera has been subsiding by about 2 or 3 centimeters per year since 2015, which is the kind of measurement you make with satellites and GPS, and which suggests gently that the system is in a quiet phase. But that is now. That is the snapshot. The chamber under Yellowstone is dynamic, and over geological time, it has not always looked the way it looks today. 2.1 million years ago, the conditions were different. The shallow chamber held a much higher fraction of melt, perhaps approaching the 50% threshold. The deeper reservoir was actively pumping fresh basalt upward into the crust above. The pressure was building. The volatiles were saturating. The roof rocks were beginning to fracture. And one day, somewhere in what is now the Island Park area, just west of the modern caldera, the system passed a point of no return. A tiny crack opened, then a larger one. Then the rock could no longer hold what was beneath it, and the largest eruption in the entire history of the Yellowstone hotspot began. We have a name for what came out of the ground that day. We call it the Huckleberry Ridge Tuff. And the scale of what it did, the scale of what an eruption like that actually means, is something most people are not prepared to absorb. 2,080,000 years ago, in what is now the corner of land where Wyoming meets Idaho, there was a morning that began like any other. The Pleistocene was young. The continents had already drifted into roughly their modern positions, but the climate was different. The wildlife was different, and our own species did not yet exist. In the forests and grasslands of what would one day become Yellowstone National Park, Mastodons grazed and ancient horses moved in herds across plains that would eventually be buried under the volcanic deposits we are about to discuss. Saber-toothed cats hunted at the forest edges. Camels, actual camels, native to North America in those days, drank from streams that would, within a few hours, cease to exist. And 5 kilometers below the surface, in a magma chamber whose existence none of those animals could have suspected, a threshold was being crossed. We do not know exactly what tipped it over. There are several reasonable candidates. New basaltic magma may have been injected from the deeper reservoir, raising the pressure in the shallow chamber past the point that the overlying rock could contain. Or the volatile content of the magma, the dissolved water and carbon dioxide, may have reached saturation, exsolving suddenly into gas bubbles that expanded with terrible force. Or a large earthquake may have fractured the roof rocks, creating a path for the pressurized magma to find. Most likely, it was some combination of all three, working together, the way large geological events usually do. Whatever the trigger was, the result is recorded in the rocks. A vent opened. The contents of the chamber began to come out, and what came out of the ground over the following weeks and months and years is what geologists today call the Huckleberry Ridge Tuff, the largest known eruption in the entire 16-million-year history of the Yellowstone hotspot. To understand how big it was, we need to think for a moment in terms of volume, which is a strange thing to do for an event of this kind because the numbers stop meaning much past a certain point. The Huckleberry Ridge eruption produced about 2,500 cubic kilometers of magma. That is the figure you will see in most textbooks, and it understates the case considerably because it does not include the additional 2,000 cubic kilometers or so of fine ash that was blown high into the atmosphere and dispersed across the continent. So the total volume of material expelled from the ground was something closer to 4,500 cubic kilometers. To compare this with something familiar, the 1980 eruption of Mount St. Helens, the eruption that flattened forests in Washington state and was, for an entire generation of Americans, the defining image of what a volcano could do. That eruption produced roughly 1 cubic kilometer of magma. The Huckleberry Ridge event was 2,500 times larger. The 1991 eruption of Mount Pinatubo in the Philippines, which cooled the entire planet by half a degree and disrupted weather patterns for years, produced about 10 cubic kilometers. Huckleberry Ridge was 250 times bigger than that. These ratios are easy to write and difficult to feel. So let me try a different angle. The eruption created a hole in the ground, what we now call the Island Park caldera, that measures 100 kilometers long and 50 kilometers wide. It is one of the largest calderas on the planet. If you superimposed it on the state of Connecticut, it would cover most of the state. If you placed it over the Sea of Marmara, the entire body of water would fit inside the crater with room to spare. The volcanic deposits the eruption left behind are, in places, 300 meters thick, the height of a 60-story building, and they extend outward from the source for hundreds of kilometers in every direction. And ash from the eruption, the fine-grained material that the wind carried up into the stratosphere and then deposited far away, has been found as far south as the Gulf of Mexico, as far east as the Mississippi River near St. Louis, and as far west as Southern California. About half of the modern continental United States was, in some way, dusted by what came out of the ground that morning. Now here is where the story takes a turn that almost nobody outside of professional volcanology knows about, and which has only become clear over the last 20 years. Until quite recently, geologists thought of the Huckleberry Ridge eruption the way most people think of any volcanic eruption, as a single, terrible event. A bad day. A few hours of catastrophe, followed by years of recovery. That image, which is the image you get from disaster films and news coverage of historical eruptions, fits well enough for ordinary volcanoes. it does not fit Huckleberry Ridge. The work of revealing what actually happened is largely the result of a New Zealand volcanologist named Colin Wilson, who has spent something like 2 decades walking through the deposits of this eruption with a notebook, mapping every layer, dating every crystal, building up an increasingly detailed picture of what the ground actually shows. And what the ground shows, when you look at it carefully, is not a single event at all. It is a sequence. Wilson and his colleagues identified 3 distinct layers of welded ash within the deposit, which they labelled members A, B, and C. Member A came first. It erupted from vents in the central part of what is now the Island Park region, and the chemistry of the rock tells us that it was fed not by a single body of magma, but by at least 9 different magma pockets, all tapping the same crustal reservoir from slightly different angles. The eruption was violent, sustained, and produced enormous volumes of pyroclastic flow, those fast-moving avalanches of hot ash and gas that destroy everything in their path. And then it stopped, or rather, it slowed dramatically. The vents quieted. Ash began to settle. In the layers of deposit Wilson examined, he found evidence of weather, wind patterns reworking the loose ash, even snowfall, which means weeks or months passed during this lull. The world around the volcano did not return to normal, but it began the long process of trying. Then, Member B erupted. This was the largest of the 3 by volume, around 1,300 cubic kilometers of fresh magma, sourced from a different vent system to the north of the original eruption area. If Member A was a catastrophe, Member B was an apocalypse. The ash flows from this phase are thicker, the deposits more extensive, the destruction more complete. And it too eventually subsided. And then there was another pause, a longer one this time, lasting years to decades, during which the eruption appeared to have ended entirely. Plants would have begun to recolonize the edges of the devastated zone. Animals, those that survived in distant refuges, might have begun moving back into the ash plains as they cooled and weathered. Streams would have re-established themselves in new channels carved through the loose volcanic debris. Life was beginning to resume. And then Member C erupted. Smaller than the first 2, but still a major event, producing volcanic deposits that buried whatever ecosystems had managed to start over. The vents this time were further south, near what is now called Red Mountains. The magma was geochemically distinct, suggesting that the original chamber had been partially refilled and reactivated. After Member C, finally, the eruption ended, and the entire region, having undergone 3 catastrophic episodes spread out over what may have been 10 or 20 or even 30 years, settled into the long quiet that would last for the next 800,000 years. Try for a moment to imagine what this would have meant for any creature living through it. If you somehow survived Member A, hidden in some cave or sheltered valley far enough from the source, you would not have known that Member B was coming. You would have lived through what felt like the worst event in the world's history, watched the sky clear, watched the temperature begin to recover, watched the first hardy plants push through the ash. And then the sky would have darkened again. And after Member B, if you lived through that too, you would have had years of relative quiet, long enough to forget, long enough to believe it was over, long enough to start a new life in the changed world. And then it would have happened again. The eruption was not a day, it was a generation. This is one of the reasons modern volcanologists are reluctant to use the word supereruption the way it is used in popular media. The events that the word describes are not single moments. They are extended sequences drawn out across timescales that we have trouble holding in our minds. And the implications of this for any future event are significant, because they suggest that an eruption at Yellowstone, if and when it ever happens again, may not be one disaster but many. a slow series of catastrophes that humanity would have to live through, adapt to, and somehow survive over years or decades. The evidence for all of this is preserved, beautifully and in detail, in the cliffs at a place called Mount Everts, just east of Mammoth Hot Springs, in the northern part of Yellowstone National Park. If you visit the park and drive north on the Grand Loop Road, you can look up at those cliffs and see two distinct layers of welded volcanic tuff stacked one on top of the other. The lower layer is the Huckleberry Ridge. The upper layer is something else, something younger, and in between them, eroded into the surface of the older deposit, are the ghost shapes of small stream valleys that formed during the long quiet between the two eruptions, then were buried when the next one came. It was at Mount Everts in the early 1960s that geologists first realized that more than one supereruption had happened in this region. Two enormous events, separated in time, stacked in plain sight on the side of a single mountain. They had been walking past it for years, and once they understood what they were looking at, the entire history of Yellowstone began to be rewritten, because Huckleberry Ridge was only the first. 800,000 years passed. That is a span of time so far outside human experience that the brain has no real way to hold it. It is roughly 4 times the age of our entire species. It is longer than the time between the present day and the last common ancestor we share with the Neanderthals. During those 800,000 years, mountain ranges shifted, river valleys carved themselves deeper, ice sheets advanced and retreated across northern continents in their long Pleistocene rhythm. Whole genera of animals rose and fell. The world that existed when Member C of the Huckleberry Ridge eruption finally went quiet was not the world that existed when the next Yellowstone caldera formed. Those two worlds had nothing in common except the same rock plume, sitting in the same place beneath the same drifting continent. When the second great eruption finally came, around 1,300,000 years ago, it happened in a different spot. The hotspot itself had not moved much, of course. The hotspot does not move. But the North American plate had carried the previous caldera somewhat to the southwest, and the new center of activity opened up in what is now the Henry's Fork region of eastern Idaho, just west of the modern park boundary. The eruption produced a rock formation called the Mesa Falls Tuff, and the caldera it created, Henry's Fork caldera, sits today as a shallow basin nested partially inside the older Island Park caldera, like a smaller bowl placed inside a larger one. If you fly over the area, you can still see the rim, although time and erosion have softened it almost beyond recognition. The Mesa Falls eruption was, by any reasonable standard, enormous. It produced about 280 cubic kilometers of magma. The Plinian column that rose above the vent in its opening hours dropped a layer of ash and pumice 5 meters thick across the Ashton area of Idaho. The kind of ash blanket that would, in any modern context, bury entire towns and render whole regions uninhabitable for a generation. Pyroclastic flows roared outward and welded themselves into a sheet of solid rock covering 2,700 square kilometers, in places more than 150 meters thick. The ash plume reached the stratosphere and dispersed eastward, leaving deposits as far away as Nebraska and Colorado and the southern Rocky Mountains. And yet, by the standards of Yellowstone, this was the small one. That is the strange thing about putting these eruptions in sequence, because the human instinct is to look for some kind of escalation or pattern, and there isn't one. Mesa Falls was about 1/9 the size of Huckleberry Ridge. It was substantially smaller, and the caldera it produced was substantially smaller too. If you ranked the 3 great Yellowstone eruptions by volume from largest to smallest, you would get Huckleberry Ridge first, then Lava Creek, which we will come to soon, and Mesa Falls last by a considerable margin. Some volcanologists, in fact, are reluctant to call Mesa Falls a true supereruption at all because it falls just below the technical threshold of 1,000 cubic kilometers of erupted material that defines the highest category on the Volcanic Explosivity Index. By that strict definition, Yellowstone has had 2 supereruptions in its modern history, not 3. Mesa Falls is something else. A very large eruption, an extraordinary eruption, but not, by the most precise terminology, in the same class as its older and younger siblings. This brings us to the part of the story that I want to spend some real time on, because it is the part that almost everyone gets wrong, and the wrongness of it has consequences for how the public understands volcanic risk in general. There is a piece of conventional wisdom about Yellowstone that you have probably encountered, perhaps more than once. It goes something like this. Yellowstone has erupted 3 times in the past 2.1 million years. The intervals between those eruptions average around 700,000 years. The last eruption was 631,000 years ago. Therefore, and this is the move that the argument depends on, the move that makes it feel persuasive, Yellowstone is overdue. The eruption is somehow late, the clock is ticking, we are living on borrowed time. This is not how geology works. It is not how statistics work either. And the reason it is wrong is worth understanding carefully, because the same pattern of thinking shows up in a lot of places, not just in conversations about supervolcanoes. Let me lay out the actual numbers first. The interval between the Huckleberry Ridge and Mesa Falls eruptions was about 800,000 years. The interval between Mesa Falls and Lava Creek, the one that built the modern caldera, was about 670,000 years. The time elapsed since Lava Creek is about 631,000 years. If you add up the first 2 intervals and divide by 2, you get an average of about 735,000 years. So the popular argument runs, we are about 100,000 years short of the average, which means an eruption is essentially due any moment now. The trouble is that you cannot establish a meaningful pattern from 2 intervals. 2 data points do not constitute a trend. They constitute 2 data points. To say that the average gap between Yellowstone eruptions is 735,000 years in any statistically meaningful sense would require dozens of intervals, perhaps hundreds, distributed over a long enough time that you could measure how much they actually vary from one another. We do not have that data. We have 3 eruptions, 2 intervals, and a wide range of plausible explanations for both. The geological systems that produce supereruptions are stochastic. That is, they are governed by chance combinations of many independent factors, and the timing of any given eruption depends on conditions that change in unpredictable ways over hundreds of thousands of years. And there is a deeper problem with the argument, which is that one of the 3 eruptions in the supposed cycle is not really comparable to the other 2. Mesa Falls, as I mentioned, was about 1/9 the size of Huckleberry Ridge. If you are looking for a pattern in true supereruptions, events that produce more than 1,000 cubic kilometers of magma, then Mesa Falls does not qualify, and you are left with just 2 events, Huckleberry Ridge and Lava Creek, separated by a gap of about 1.5 million years. From 2 events you get 1 interval. From 1 interval, you get exactly 0 ability to predict when the next event will happen. You have, statistically speaking, no information at all. This is the official position of the United States Geological Survey, which has said as much in writing many times. The intervals between Yellowstone's major eruptions show no statistically significant pattern. The system is not periodic. There is no clock ticking. The annual probability of a major eruption at Yellowstone, calculated from the available evidence, is something like 1 in 700,000. And even that figure, as the USGS itself notes, is probably an overestimate for the short term. because there is no evidence that the magma system is currently in a state that could produce such an eruption. Look at it this way. Suppose you flip a coin and it comes up heads. Then you flip it again after waiting an unknown amount of time, and it comes up heads again and again. 3 heads in a row. Could you, from this, predict when the next heads will appear? Of course not. The coin has no memory. Each flip is independent of the others. The pattern in the timing of those 3 heads is not a pattern. It is just what happens when you flip a coin a few times. And while a magma chamber is far more complex than a coin, the principle is similar. The past timing of eruptions tells you almost nothing about the timing of the next one. What tells you something? What tells you almost everything is the current state of the magma system. And the current state of the magma system, as we discussed, is largely solid rock, with a melt fraction nowhere near the threshold required for catastrophic eruption. There is one more thing to say about Mesa Falls before we move on, and it concerns the broader history of the hotspot. Yellowstone is not the first place this hotspot has built calderas. Before Yellowstone, the hotspot sat under a region of eastern Idaho called the Hidden Volcanic Field, and there it produced 4 large caldera-forming eruptions over a period of about 2 million years. The youngest of those, called the Kilgore Tuff, erupted about 4.5 million years ago and was enormous, around 1,800 cubic kilometers. After Kilgore, Hydra went quiet. The hotspot moved on, in a manner of speaking. The plate continued to slide southwestward over the stationary Plume, and the area of active magmatism shifted to what is now Yellowstone. Hydra has not erupted since. It probably never will again. The chamber cooled, the magma solidified, and what was once a region of catastrophic volcanism became a quiet agricultural valley where farmers raise potatoes and barley. There is some evidence that Yellowstone may be in the late stages of its own version of this same cycle. The geochemistry of the most recent eruptions shows certain isotope signatures that resemble what we see at the end of the Hydra sequence, suggesting that the upper crust has been substantially depleted by the previous 3 caldera-forming events. If that interpretation is correct, and it is one interpretation, not the only one, then Yellowstone may be approaching the end of its eruptive life, with perhaps one more major event ahead of it, or perhaps none. The hotspot itself will keep moving. A new center of volcanism will eventually open further to the northeast. And what we currently call Yellowstone will, over the next few million years, become quiet in the way that Hydra is quiet, and the way that all the older calderas along the Snake River Plain are quiet. So the picture that emerges when you look at the 3 great Yellowstone eruptions together is not one of impending catastrophe, but of a system that has been winding down for a very long time. Each eruption smaller than the last, the geochemistry shifting, the magma supply diminishing. This is not a guarantee of safety. The system could surprise us. Stochastic processes do not care about our expectations of them. But it is the opposite of the picture that gets painted in popular media, where Yellowstone is always on the verge of going off, always overdue, always one good earthquake away from ending civilization. We have one more eruption to discuss in this triplet, and it is the most important one for understanding modern Yellowstone, because it is the one whose crater you can still walk inside today. It is the one that built the place we visit. It is the youngest of the 3, the most studied, and in many ways the most revealing. It happened 631,000 years ago, and like Huckleberry Ridge before it, it turned out to be far more complicated than anyone initially realized. If you have ever visited Yellowstone National Park, you have stood inside a crater. You may not have realized this at the time. Most visitors don't. The crater is too large to perceive from the ground, the way you cannot perceive the curvature of the Earth from a beach, because the curvature is operating on a scale that exceeds the resolution of the human eye. The Yellowstone caldera is 55 kilometers wide and 80 kilometers long. It contains within it almost all of the famous landmarks people travel to see. Old Faithful, the Grand Canyon of the Yellowstone, Yellowstone Lake, the Norris Geyser Basin, the Hayden Valley where the bison herds gather in summer. All of it sits inside a depression in the Earth's surface that was created in a single eruptive sequence 631,000 years ago, when a magma chamber the size of a small mountain range emptied itself onto the landscape, and the ground above it collapsed into the void it left behind. This is the Lava Creek eruption, the third and most recent of the great Yellowstone events, and although it was smaller than Huckleberry Ridge by more than half, it is in many ways the most important of the three for understanding what Yellowstone actually is, because it is the eruption whose deposits are still visible everywhere you look. It is the eruption that built the modern landscape. Every hot spring you walk past, every geyser you wait for, every rainbow-colored pool with its bands of orange and yellow bacteria, all of that exists because of what happened that day in the long aftermath of an event that almost no one alive today can really comprehend. We know more about Lava Creek than about either of the earlier eruptions, partly because it is more recent and the deposits are better preserved, and partly because it is the focus of intense ongoing study by the US Geological Survey and a handful of academic institutions that have made Yellowstone the most thoroughly monitored volcanic system on the planet. We know, for instance, that the magma chamber that fed the eruption was about 3 to 6 kilometers deep. We know it contained two distinct bodies of rhyolitic magma, slightly different in chemistry, that geologists have labeled simply members A and B, following the same naming convention used for Huckleberry Ridge. We know the temperature of the magma at the moment of eruption was somewhere between 790 and 815 degrees Celsius. And we know, this part has only become clear in the last decade or so, that the eruption was not a single sudden event, but a sequence of events, beginning with smaller precursor eruptions that may have started years or even decades before the main catastrophe, building toward the climactic emptying of the chamber that carved the modern caldera. Let me try to describe what happened, beginning with the morning the main eruption began. Imagine a quiet day in what is now the central part of Yellowstone National Park. The forests are unrecognizable to modern eyes. The climate of 600,000 years ago was different. The species composition was different. The entire continent looked different. But the place is recognizable in its general topography. Mountains to the west and south, forests of pine and fir on the slopes, rivers running clear and cold over volcanic rock, animals moving through the trees. None of those animals know what is about to happen because there is no warning that any animal could understand. Below them, in the magma chamber, the conditions for an eruption that have been building for hundreds of thousands of years finally come together. Something gives. A crack opens in the roof of the chamber. The pressurized magma rushes upward, and within minutes, the surface of the ground in this remote corner of what would much later become the United States is splitting open, and the contents of the chamber are coming out. The first phase is what volcanologists call Plinian, named after Pliny the Younger, who described the eruption of Vesuvius that destroyed Pompeii. A column of ash and gas and fragmented rock shoots vertically into the atmosphere, driven by the explosive expansion of dissolved volatiles as they reach lower pressure near the surface. At Lava Creek, that column reached more than 30 kilometers in altitude. To put that in perspective, commercial airliners cruise at around 11 kilometers. The Plinian column from this eruption was almost 3 times higher than the planes you take for granted, punching straight through the troposphere and into the stratosphere, where the wind systems that govern weather give way to the calmer, drier air of the upper atmosphere. Within hours, that column did what Plinian columns always eventually do. It collapsed. The mass of material being driven upward became too heavy for the gas thrust to support, and the entire column began to fall back toward the Earth. But it did not fall as ash settling out gently from the sky. It fell as pyroclastic flows, dense, ground-hugging avalanches of hot gas, ash and pumice that move outward from the volcano at speeds of 100 to 300 meters per second. 300 meters per second? That is 1,080 kilometers per hour. Faster than any commercial vehicle, faster than the speed of sound in cold air. There is nothing on the ground that can outrun a pyroclastic flow. Nothing that can survive being inside one. The temperature within these flows can exceed 600 degrees, hot enough that the deposits they leave behind weld themselves into solid rock as they cool, fusing layers of ash and pumice into a single dense formation that geologists call ignimbrite. The pyroclastic flows from Lava Creek covered an area of roughly 7,500 square kilometers, in places hundreds of meters thick, burying everything within their reach beneath a tomb of fused volcanic glass. Forests vanished in seconds. Lakes boiled and then evaporated and then were covered. Whatever animals had been in the area at the moment the eruption began ceased to exist in any meaningful biological sense. They were not killed in the way we usually mean the word, with bodies left behind to decompose. They were simply incorporated into the rock, and the rock that records all of this is still there today. You can see it in the cliffs along the Gibbon River. You can see it at Tuff Cliff. You can see it in the canyon walls at Virginia Cascade. The Lava Creek Tuff is the bedrock of much of the modern park. We walk on it, we hike past it. It is the literal foundation of the place. While all of this was happening at the surface, something equally consequential was happening underground. As the magma chamber emptied, and emptied it did, releasing about 1,000 cubic kilometers of material in a span of weeks to months, the rock that had been resting on top of it lost its support. The roof of the chamber collapsed. Not all at once, but in stages, in great blocks and segments that dropped downward into the void where the magma had been. This is the process that creates a caldera. The word itself comes from the Spanish for cooking pot, and the analogy is apt enough, a basin formed when the ground falls in on itself. By the time the eruption was over, the caldera was complete. 55 kilometers across in one direction, 80 in the other, hundreds of meters deep in places. A vast new feature on the landscape of North America formed in a matter of weeks. But the caldera was not empty for long, because the same heat that had driven the eruption was still there. The magma chamber, partially drained but not destroyed, continued to provide thermal energy to the rocks above. Groundwater began to seep into the new fracture systems that the collapse had created. The great curving faults around the rim of the caldera, the cracks running through the broken floor. That water, meeting hot rock at depth, did what water always does when it meets hot rock. It heated, it rose, and as it rose, it found pathways to the surface, channels through the shattered crust where pressurized hot water and steam could escape. Those channels became the geyser basins. Those geyser basins became Old Faithful and Norris, and the Upper Geyser Basin, and all the rest. Every single hydrothermal feature in modern Yellowstone exists because of the geological architecture that the Lava Creek eruption left behind. The hot springs are not separate from the volcano. They are the volcano in its quiet phase, doing what a magma chamber does when it has stopped erupting, but has not yet stopped being warm. In the immediate aftermath of the eruption, things stayed quiet for a long time. For perhaps 50,000 years, there were no further eruptions inside the caldera at all, while the system cooled from its post-eruptive state towards something closer to equilibrium. Then, gradually, smaller eruptions began. Lava flows of rhyolite, thick, slow, viscous flows of partially crystallized magma, pushed up through the caldera floor and built broad domes and ridges. Some of these flows were enormous in their own right, 50 or 100 cubic kilometers each, dwarfing anything that has erupted in human history. They form much of the topography you see when you drive across the central part of Yellowstone today. The Pitchstone Plateau is one of these flows. So is the Madison Plateau. The whole interior of the caldera has been progressively repaved by volcanic activity since the original collapse, although the rim of the original crater is still visible if you know where to look, most clearly at the steep cliff face at Madison Junction, where a half-kilometer high wall of rock marks the boundary between what dropped and what did not. The last lava flow inside Yellowstone happened about 70,000 years ago. Since then, the surface has been quiet. There have been earthquakes. There are always earthquakes, 1,500 to 2,500 of them every year, almost all of them too small to feel. There have been hydrothermal explosions, some of them substantial, the kind we will come to in detail later on. But no magma has reached the surface in 70,000 years, which means the entire history of Yellowstone as a magmatic feature has been inactive for a span of time longer than the entire history of behaviorally modern humans. We have been here, telling stories and making art and burying our dead for perhaps 50,000 years. The volcano under our feet has been silent for longer than that. Whether it stays silent is a different question. The magma chamber is still there. The plume is still rising. The system that produced 3 of the largest eruptions in the geological record is still, in its slow and patient way, capable of doing it again. What we need to understand now is what would actually have to happen for that to occur. What the trigger is, what the sequence of events looks like, what conditions inside the chamber would need to change. Because the eruption is not waiting on a calendar, it is waiting on physics. Physics, when you look at it carefully, is mostly a story about thresholds. Water does not gradually become ice as it cools. It stays liquid through an enormous range of temperatures, and then, at 0 degrees Celsius, it crosses a line and becomes something else. A bridge does not slowly bend into collapse under increasing weight. It holds, it holds, it holds, and then at some specific load, it fails completely. The world is full of these transitions, points at which a system that has been behaving one way for a long time suddenly behaves another way, and the suddenness of the change has nothing to do with how slowly the underlying conditions arrived at it. A magma chamber works the same way. It holds for hundreds of thousands of years, and then it doesn't, and the moment it stops holding is governed by a small number of physical conditions that all have to align. There are essentially 4 of them. 4 conditions that, taken together, determine whether the chamber under Yellowstone is capable of producing a major eruption at any given moment in its history. None of them is sufficient on its own. All of them have to be met. And right now, as far as we can measure, none of them are met at the levels that would matter. Walking through what they are and why they matter is probably the clearest way to explain why the supervolcano you have heard so much about has not erupted in 631,000 years and is not going to erupt tomorrow either. The first condition is the one we have already touched on, and it is the most important. The melt fraction in the magma chamber has to be high enough for the magma to mobilize. We talked earlier about how the chamber under Yellowstone is mostly solid rock, with melt distributed through it like water in a sponge, currently somewhere between 5 and 15% liquid. To produce a major eruption, that fraction needs to climb past 50% and probably higher. Below that threshold, the crystals in the chamber are touching each other, supporting each other, holding the structure rigid. The melt cannot move because the framework of solid material around it does not allow it to move. It is like trying to pour honey out of a jar that is also full of marbles. You can tip the jar all the way over, and almost nothing will come out because the marbles are in the way. To make the magma flow as a fluid, you need to dissolve enough of those marbles that the liquid can find its own path. And dissolving them requires more heat, sustained over thousands of years, delivered from below by fresh injections of basalt from the deeper reservoir. The heat is patient. It is also, at the moment, not arriving in anything like the necessary quantity. The second condition has to do with what is dissolved in the magma itself. Magmas always contain dissolved gases, water vapor, carbon dioxide, sulfur compounds, smaller amounts of other things. And those gases stay dissolved as long as the pressure on the magma is high enough to keep them in solution, the way carbon dioxide stays dissolved in a sealed bottle of soda. Reduce the pressure and the gas comes out. This is the principle that makes any volcanic eruption explosive in the first place, because as magma rises through the crust toward lower pressure, the dissolved volatiles begin to exsolve, forming bubbles, and those bubbles expand, and the expanding bubbles drive the magma upward faster, which lowers the pressure further, which drives more exsolution in a runaway feedback that ends with a Plinian column 30 kilometers high. But for that runaway to start, the magma has to be saturated with dissolved gas in the first place. It has to be carrying enough water and carbon dioxide that, when the pressure drops, there is something to come out. The volatile content of the magma under Yellowstone right now is not well known, but the indirect measurements we have suggest it is below what would be required to drive a catastrophic event. The chamber would need to absorb more volatiles, probably from new basaltic injections, before the explosive potential reached a dangerous level. The third condition is about the rocks above the chamber, the ones that form what geologists call the roof. A magma chamber sitting in the upper crust is held in place by the weight of everything above it, kilometers of rock pressing down, generating what is called lithostatic pressure, the pressure of the lithosphere itself. As long as the pressure inside the chamber stays below the lithostatic pressure, the magma stays put. It cannot break out, because the rock above is too strong and too heavy to allow it. But if the pressure inside the chamber grows high enough, through the addition of more magma, through the exsolution of dissolved gases, through whatever mechanism, eventually it can exceed the strength of the overlying rock and force a path upward. The rock fractures, the magma escapes, the eruption begins. This is, in a sense, the most direct of the four conditions, because it is the one that actually triggers the visible event. The other three conditions create the situation in which the rock breaks. The breaking itself is what we see. The fourth condition is, paradoxically, the smallest. It is the trigger, the one event that, at the moment when all the other conditions are already met, finally pushes the system across the line. This could be almost anything, and that is part of what makes it hard to predict. It might be a large earthquake, fracturing the roof rocks at a critical moment. It might be a fresh injection of magma from below, suddenly raising the pressure in the chamber past the threshold. It might be the slow growth of crystals in the cooling parts of the chamber, which excludes water from the solid phase and thereby concentrates volatiles in the remaining melt, raising gas pressure in a process that has been called second boiling. Or it might be something else entirely, some combination of small disturbances that in retrospect will look like the first domino in a chain. We will not know until we have an event to study, which we have not had since the invention of seismometers, and so cannot fully reconstruct. The trigger is the part of the system about which we know the least, because the geological record records the eruption, not the immediate cause of it. What we can say is that the trigger does not matter unless the other three conditions are already met. You can subject the current Yellowstone chamber to all the earthquakes you want, all the small magma injections, all the fluctuations in groundwater and gas, and you will not get an eruption. The system is locked. The melt fraction is too low. The volatiles are not saturated. The roof is not under critical stress. There is no lever long enough to move the chamber out of its current state because the conditions that would make it movable do not exist. To get an eruption, you need to slowly, over thousands or tens of thousands of years, change those conditions. You need to deliver more heat from below. You need to inject more volatile-rich magma. You need to push the system through patient and consistent input toward the place where a small disturbance can cause a large effect. This is what was happening in the long build-up to the Lava Creek eruption. For perhaps 500,000 years, fresh basalt was being injected into the lower crust beneath what is now Yellowstone, slowly heating the rhyolitic chamber above, gradually raising its melt fraction, accumulating volatiles. The system was being prepared. By the time the eruption actually began, 631,000 years ago, all four conditions were in place: a high melt fraction, saturated volatiles, stressed roof rocks, and then, finally, whatever the specific trigger was, we do not know, the system released. And what had taken 500,000 years to build came out in a matter of weeks. Watching this sequence in the geological record is a strange experience because it shows you how slow the buildup is and how fast the release is. And the asymmetry between those two timescales is one of the deeply unintuitive features of how the planet actually works. We are wired by evolution to think in human timescales, days and months and years, with maybe a vague awareness of decades and centuries. We are not wired to think in spans of 500,000 years, slowly accumulating heat, slowly raising temperatures, slowly approaching a threshold that we cannot see. The chamber under Yellowstone has been in a slowly cooling phase for the last 70,000 years, since the most recent lava flow inside the caldera. The trend is clearly downward. The system is moving away from the conditions that would produce another major eruption, not toward them. To reverse that trend would require something to change at depth, a new pulse of basalt from the Plume, sustained over a long time. And there is no current evidence of any such change. So when we say that an eruption at Yellowstone is unlikely in any human-relevant time frame, we are not waving the question away. We are looking at the four conditions, measuring each of them as best we can, and noting that they are all currently far from the values that would produce a catastrophic event. The system is not poised. The threshold is far away. The physics that would have to operate to make a supereruption possible is not operating right now and would have to be set in motion by changes at depth that take tens of thousands of years to develop. This is not a guarantee that nothing will ever happen at Yellowstone. It is a description of why nothing is happening at Yellowstone right now. But when an eruption does happen, at Yellowstone or at one of the other supervolcanic systems on Earth, of which there are several, there is a feature of how the resulting ash spreads that nobody really understood until quite recently. The standard models of how volcanic ash disperses across a landscape were developed for ordinary eruptions, the kind of moderate Plinian events we have seen in the historical record. They do not work for events of the magnitude we are talking about here. A truly large eruption does something to the atmosphere that smaller eruptions cannot do. It creates its own weather, and the consequences of that, for any modern country sitting downwind of such an event, are different from what most people imagine. For most of the 20th century, when scientists wanted to predict where ash from a volcanic eruption would land, they used a model that essentially treated the eruption as a tall chimney. Hot material goes up out of the chimney, the prevailing winds at altitude take that material and carry it downwind, and the ash falls out of the sky in a long, narrowing fan that points away from the source in whatever direction the wind happens to be blowing. This model works reasonably well for ordinary eruptions. The 1980 eruption of Mount St. Helens, for instance, sent its ash on an east-northeast trajectory across Washington and Idaho, exactly as the prevailing westerly winds at the time would predict. Mount Pinatubo in 1991 dispersed ash westward across the South China Sea because it was caught up in the seasonal monsoon circulation. The pattern is almost always the same. A fan, opening downwind, narrowing as it gets farther from the source, with the heaviest deposits close to the volcano and progressively thinner deposits as you move outward. For ordinary eruptions, this is correct. For super eruptions, it turns out to be wrong in a fundamental way, and the wrongness was not really understood until 2014, when a small team of researchers at the United States Geological Survey published a paper that quietly upended decades of assumptions about what happens to the atmosphere during the largest eruptions on Earth. The lead author was a man named Larry Mastin, who works at the Cascades Volcano Observatory in Vancouver, Washington. Mastin had spent years developing a sophisticated computer model called ASH 3D, which simulates the transport and deposition of volcanic ash across three-dimensional, time-evolving wind fields. The model had been used successfully to forecast ash dispersal from a number of moderate eruptions in Alaska and elsewhere. But when Mastin and his colleagues, Alexa Van Eaton and Jacob Lowenstern, tried to apply the same model to a hypothetical Yellowstone supereruption, they ran into a problem. The standard equations did not produce results that matched the geological evidence. The ash deposits from the actual Lava Creek eruption 631,000 years ago are distributed in a pattern that no standard ash fan model could replicate. They cover too much area. They extend too far in the wrong directions. And in some places, particularly upwind of the source, they are far thicker than any traditional model would predict. This led Mastin and his team to think about something that had been mostly overlooked in earlier work. When an eruption is large enough, the column of ash and gas it produces does not simply rise to a certain altitude and then disperse. It rises. And then, when it can rise no further because the surrounding atmosphere has become too thin to support continued ascent, it spreads horizontally in all directions, forming a vast, flattened cloud of suspended ash that geologists call an umbrella cloud. The cloud is named for its shape because it does look something like an umbrella, with a vertical stem of rising material feeding a broad horizontal canopy at the top. And here is the critical thing about umbrella clouds, the thing that changes everything about how we understand large eruptions. They do not move with the wind. They move against it. This sounds almost impossible at first. Wind always wins, doesn't it? When you blow on a candle, the flame goes the way you blow it. When a tornado meets a steady ambient breeze, the breeze does not push the tornado around, but supereruption umbrella clouds are different because they are not simply being passively pushed around by atmospheric currents. They are an atmospheric current. The mass of material being injected into the stratosphere by a major eruption is so enormous that it generates its own pressure gradient, a localized high-pressure zone that drives the cloud outward in every direction at once. The expansion is faster than the prevailing winds. The cloud pushes them aside. It expands radially, like ink dropped into still water, regardless of which way the wind happens to be blowing on any given day. The result is that ash from a supereruption does not get deposited in a fan pointing downwind. It gets deposited in something much more like a target, with the source at the center and roughly concentric rings of decreasing thickness extending outward in all directions. Mastin's team simulated 3 different versions of a Yellowstone supereruption, one lasting 3 days, one lasting a week, one lasting a month, and ran each simulation under modern atmospheric conditions using actual wind data from recent years. In every case, the resulting ash distribution looked like a target. heavy in the center, lighter in the middle distance, a thin, dusting out at the edges. And the edges reached far beyond what anyone had previously imagined possible for the modern North American continent. Let me give you the numbers, because they are the kind of numbers that change how you think about geographical scale. In the Marston team's modeling, the area within 500 kilometers of Yellowstone, which includes the entire state of Wyoming, much of Montana and Idaho, and the northern portions of Utah and Colorado, would receive ash deposits measured in meters, in some places several meters thick. This is not a layer you sweep off your driveway. This is a layer that buries roads, collapses roofs, and renders entire regions uninhabitable for the foreseeable future. The cities of the northern Rocky Mountains, including Salt Lake City and Denver and Boise, would be smothered under enough ash to fundamentally end their function as cities. Not damaged. Ended. Beyond 500 kilometers, the deposits get thinner, but they remain enormous. The model shows ash thicknesses of 10 to 30 centimeters extending across most of the upper Midwest. Cities like Minneapolis and Chicago and Kansas City would receive what is essentially the equivalent of a heavy snowstorm made of glass-laced grit, except that this storm does not melt and does not blow away. It just sits there, and ash, unlike snow, is not water. It does not evaporate. It does not drain into rivers and disappear. It has to be physically removed, scoop by scoop, truckload by truckload, and there is nowhere to put it. The cleanup cost alone for a continental ash deposit of this magnitude would be unmeasurable in any meaningful way, because it has never happened in the industrial era, and there is no comparable event to estimate from. Out at the periphery in the eastern United States, on the Atlantic seaboard, in cities like New York and Atlanta and Miami, the deposits would be measured in millimeters rather than meters. A few millimeters of ash sounds trivial when you say it out loud. It is not trivial. A few millimeters of fine volcanic ash is enough to ground all aircraft, because it gets sucked into jet engines and melts and resolidifies on the turbine blades and stops them from working. We saw this in 2010 when the Eyjafjallajökull eruption in Iceland, which was small by any standard you care to apply, shut down European air travel for nearly a week and cost the global aviation industry roughly $2.5 billion. Eyjafjallajökull was a fraction of a percent the size of what we are discussing here. A modern Yellowstone eruption would shut down North American air traffic completely, and the shutdown would not last a week. It would last months, possibly longer. The deposits would also damage electrical infrastructure across most of the continent. Volcanic ash, especially when it gets damp, conducts electricity. It clings to the insulators on high-voltage transmission lines and causes flashover events that knock substations offline. It clogs the cooling systems on power plants. It corrodes electrical contacts. The grids that keep modern cities functioning would fail in cascading patterns across thousands of kilometers of territory, and the failures would compound on each other, because you cannot easily repair an electrical grid in a city where the streets are buried in volcanic ash and there is no way to drive a maintenance truck to the broken substation. Drinking water systems would be contaminated, both because the ash itself contains soluble elements that are toxic in concentration, and because the filtration systems at municipal water plants are not designed to handle the kind of particulate load that would come pouring in from rivers carrying ash off the landscape. Agriculture across the entire central plains of the United States, the breadbasket of an enormous portion of the world's grain supply, would be effectively destroyed for at least one growing season, possibly several. The economic shock alone would be without precedent. And all of this is the result of the umbrella cloud, the thing that nobody fully appreciated until Mastin and his team did the math properly in 2014. A normal eruption sends ash downwind. A supereruption sends ash everywhere. The geological evidence for this is right there in the deposits from Lava Creek, which extend in directions that no ordinary downwind model could explain. We can find Yellowstone ash in California. We can find it in Iowa. We can find it in Louisiana, 1,500 kilometers south of the source. The Hotspot has been distributing material across the continent in this radially symmetric way for the entire history of its eruptions, and it has been doing so because the physics of really large eruptions is not the physics of small ones. Past a certain scale, the rules change. This is the part of the story where, if we were going to encounter genuine catastrophe in human terms, we would encounter it. The ash that settles on cities, the infrastructure that fails, the grain that does not get harvested, the aircraft that cannot fly. None of this is speculation. All of it is the direct result of mechanisms we now understand, applied to a kind of event that the geological record shows happens at this site every few 100,000 years on average. It would not end humanity. We have weathered worse. But it would, in a matter of weeks, reshape the lives of every person on the affected continent, and the effects would persist for generations. But the ash, terrible as it is not actually the worst part. The worst part is what comes after the ash settles. The worst part is the gas. In April of 1815, on the island of Sumbawa, in what is now Indonesia, a mountain that had been quiet for centuries began to make sounds that the people living around it had never heard before. The sounds came from deep underground, low rumblings that seemed to travel up through the rock itself, and they grew steadier and louder over a period of weeks. The mountain was called Tambora. By the standards of the planet's truly great eruptions, what happened next was a small event. By the standards of recorded human history, it was the largest volcanic eruption that any living person had witnessed, and the largest that anyone alive today has ever read about. On the evening of April 10th, Tambora detonated. The eruption column rose more than 40 kilometers into the atmosphere. Pyroclastic flows rushed down the mountain's flanks and into the surrounding sea, killing everyone in the immediate area. Ash fell across an area of 2 million square kilometers, in places thick enough to collapse roofs in cities 1,000 kilometers away. The blast was heard in Sumatra, 2,600 kilometers distant, where confused British colonial officials assumed it was the sound of cannon fire from some unknown naval engagement and dispatched ships to investigate. Tambora produced about 100 cubic kilometers of magma. That is roughly 1/10 the volume of the Lava Creek eruption, the smallest of Yellowstone's 3 great events. By the standard scale used to rank explosive eruptions, Tambora was a magnitude 7 on a scale where Yellowstone events register as magnitude 8, which sounds like a small difference until you realize that each step on the scale represents a 10-fold increase in the volume of material erupted. So Tambora was about 1/10 the size of the smallest Yellowstone supereruption. And Tambora, in the months and years that followed, killed perhaps 100,000 people across the globe, most of them very far from Indonesia, most of them never aware of what had happened on Sumbawa or what it had to do with them. The mechanism by which a volcano on one side of the planet kills people on the other is the mechanism we need to understand, because it is the mechanism that would matter in the modern world if Yellowstone ever did what Yellowstone has done before. The mechanism is gas. Specifically, it is sulfur dioxide. Every large volcanic eruption injects gases into the atmosphere alongside the ash and the rock fragments. Most of those gases are familiar: water vapor, carbon dioxide, hydrogen sulfide, smaller quantities of various other compounds. But the most consequential of them, by a considerable margin, is sulfur dioxide. The reason it matters is that sulfur dioxide, once it reaches the stratosphere, undergoes a slow chemical reaction with water vapor to form sulfuric acid aerosols, tiny droplets of acid suspended in the upper atmosphere, each one too small to see, but together forming a layer that can persist for years. The aerosol layer reflects sunlight. It reflects a small but significant fraction of the solar radiation that would otherwise reach the surface of the Earth, and as a result, the planet beneath it cools. This is not a hypothesis. This is something we have observed directly with instruments in the modern era. The Mount Pinatubo eruption in 1991 injected about 20 million tons of sulfur dioxide into the stratosphere. Within a few months, the resulting aerosol layer had spread around the globe, and over the following 2 years, global average temperatures dropped by about half a degree Celsius. Half a degree sounds trivial in conversation, but in climate terms, it is enormous. It is roughly the same magnitude as the warming the planet has experienced over the entire industrial era, applied in reverse in the space of a few months. The cooling persisted for about 3 years before the aerosols eventually settled out and conditions returned to normal. Crops failed in some regions. Weather patterns shifted in ways that produced drought in places that should have been wet and floods in places that should have been dry. People died who would not otherwise have died, and Pinatubo was, by historical standards, a moderate event. Tambora, in 1815, injected an estimated 60 million tons of sulfur into the stratosphere, roughly 6 times what Pinatubo would put up there nearly 2 centuries later. The cooling that followed was correspondingly more severe. Global average temperatures dropped by something like 0.7 of a degree Celsius, which sounds like a small number but which, distributed across the planet in unequal ways, produced consequences that historians are still cataloguing. The summer of 1816 became known in much of the Northern Hemisphere as the year without a summer. In New England, frost killed crops in June. In Vermont, snow accumulated in the fields in early summer and remained on the ground for days. Across Europe, where the population was already suffering from the disruptions of the Napoleonic Wars, the harvest failed almost completely. Wheat prices in France and Germany doubled, then tripled. Bread riots broke out in cities across the continent. In Ireland, where the potato crop failed for the first time in living memory, the first warning of the much greater famine that would come 3 decades later, typhus epidemics swept the countryside, killing tens of thousands. In China, the monsoon weakened, the rice harvest collapsed, and famine spread through the southern provinces for 3 consecutive years. In India, the disruption of the monsoon produced conditions in which a new strain of cholera emerged from the Bay of Bengal and began the long migration that would eventually carry it across most of the world. 100,000 deaths is the conservative estimate for what Tambora did. The real figure, when you account for the secondary effects, the famines and the disease outbreaks, and the wars that broke out over food in regions already destabilized, is probably much higher, possibly 3 or 4 times higher. We will never know precisely because record-keeping in 1816 was what it was, and the deaths from cholera and typhus and starvation were not always recognized at the time as connected to a volcano nobody in Europe had ever heard of. On an island most Europeans could not have located on a map. Now let me put Yellowstone in the same scale. A modern Yellowstone eruption on the order of the Lava Creek event would inject several 100 million tons of sulfur into the stratosphere. Not 60 million, several 100 million. 5 times Tambora at the low end, perhaps 10 times Tambora at the high end, though the precise figure depends on details of the eruption that we cannot predict in advance. The aerosol layer that would form in the stratosphere afterward would be substantially denser, more reflective, and much longer lived than anything humanity has experienced in recorded history. There is genuine scientific disagreement about how much cooling this would produce. Some climate models suggest a global average temperature drop of 1.5 degrees Celsius. Others suggest as much as 4 to 8 degrees. A 2024 study from NASA's Goddard Institute argued that the upper estimates may be too high because the aerosol particles in such an event might grow large enough to reduce their reflective efficiency. Other recent work, looking at the geological record of the Toba supereruption 74,000 years ago, suggests cooling of 2 to 4 degrees lasting for 5 years or more. What everyone agrees on, regardless of where they fall in the modelling debate, is that the agricultural consequences would be severe and prolonged. Even the most optimistic scenarios show growing seasons across the temperate northern hemisphere shortened by weeks. Even the lower estimates produce frost events deep into what should be summer months across the wheat belts of North America, the rice-growing regions of Southeast Asia, the bread-producing plains of Central Europe and the Black Sea. The world's agricultural system, which currently feeds more than 8 billion people, is not built to withstand a sustained reduction in growing season of even a few weeks across multiple consecutive years. The system depends on the regularity of seasons. Disrupt that regularity for 2 or 3 years, and the consequences cascade through grain markets and food prices and political stability in ways that are difficult to model and impossible to fully prevent. This is what makes the volcanic gas, more than the volcanic ash, the truly globe-spanning consequence of a major eruption. The ash falls within a few thousand kilometers of the source. It is a continental-scale problem. The gas, by contrast, gets carried into the stratosphere, where it spreads around the entire planet within a few months. There are no neighborhoods that escape. There is no continent so far from Yellowstone that the eruption would not affect it. The aerosols circle the globe, and the cooling falls on every part of the surface beneath them, and the harvests fail wherever they happen to be growing, and the food prices rise wherever food is sold, and the political consequences play out in every country that has citizens who need to eat, which is all of them. The historical record of Tambora and the much larger historical record of Toba gives us a basic outline of what to expect. Cooling for several years, famine in marginal agricultural regions, disease outbreaks following the famine, mass migration where migration is possible, mass death where it is not. Disruption of weather patterns, including monsoons, with effects that extend far beyond the climatic anomaly itself. Recovery over a span of about a decade, by which time the aerosols have settled out and temperatures have returned to baseline, but the social and economic consequences continue to ripple through the affected populations for generations afterward. Humanity, for what it is worth, would survive. We have survived worse. The Toba eruption, 74,000 years ago, is sometimes proposed as the cause of a genetic bottleneck in early human populations, although the evidence for this is contested, and recent work suggests that early humans in many regions actually persisted through that event without significant population decline. We are a remarkably resilient species, and our agricultural and technological systems, while fragile in some ways, are far more capable of buffering large shocks than anything our ancestors had access to. A modern Yellowstone eruption would not be an extinction event, it would be a catastrophe. Those are different things. And the question that comes after is the obvious one, the one that everyone who has thought about Yellowstone for more than a few minutes eventually arrives at. How likely is any of this to actually happen in any time frame that matters to a person currently alive? The answer requires us to think carefully about probability, not the kind of probability that gets used in news headlines, but the kind that comes from looking at the geological record honestly and asking what it actually tells us. And what it tells us, when you do the calculation properly, is something most people find surprising. The official figure, the one the United States Geological Survey has settled on after decades of careful work, is 1 in 700,000. That is the annual probability of a major eruption at Yellowstone, calculated from the available evidence and refined over many years by the scientists who study the system most closely. It is a small number, It looks even smaller when you write it out as a percentage, about 0.00014% in any given year, and smaller still when you compare it to the kinds of risks people actually pay attention to in their daily lives. But raw numbers like this, by themselves, do not tell you very much. To make sense of a probability, you have to put it next to other probabilities. You have to find a way of feeling what it actually means. Let me try to give you a frame for it. Imagine you are a person of average lifespan, somewhere between 70 and 80 years. Over the course of your entire life, the probability that Yellowstone will produce a major eruption is something like 1 in 9,000. Roughly. The math is simple. 80 divided by 700,000, and the result is the kind of small number that we are not particularly good at interpreting. 1 in 9,000 is the kind of probability that if you encountered it as a risk on a medical procedure, you would probably proceed without much hesitation. It is the kind of probability that, for a baseline event in your life, simply does not enter your daily calculations. It does not affect how you decide where to live, what to eat, who to spend time with. It is, statistically speaking, the kind of risk you simply absorb without noticing. For comparison, the lifetime probability that an average person will be killed by an asteroid impact is somewhere around 1 in 1,600,000, depending on how you count it. That sounds reassuringly tiny, but if you compare it directly to Yellowstone, you find that asteroid death is, statistically, about 5 times more likely than dying because of a Yellowstone eruption during your lifetime. This will surprise most people. The cultural prominence of the supervolcano story, the disaster films, the late-night documentaries, the breathless coverage every time a few earthquakes happen in Wyoming. All of this has created the impression that Yellowstone is a major and imminent risk. By the actual numbers, it is a smaller threat than a rock from space. There are bigger risks that almost everyone overlooks. The lifetime probability of dying in a car accident for someone in a developed country is something like 1 in 100. The lifetime probability of dying from heart disease is closer to 1 in 5. The mathematical universe of things that are statistically likely to actually affect you is dominated almost entirely by ordinary causes, diseases, accidents, the slow accumulation of cellular damage that makes mortality a near certainty over a long enough timescale. Yellowstone does not appear in that universe. It is a tail risk, the kind of thing that exists in the far edge of the probability distribution, real enough to take seriously, but not real enough to organize your life around. But the 700,000-year figure deserves a closer look because the way it gets calculated tells you something important about the limits of what we know. You start with the geological record. You count the major eruptions in the past, you measure the time between them, you take an average, and you assume the future will resemble the past. That is the basic logic. For Yellowstone, the past contains 3 caldera-forming eruptions over roughly 2.1 million years, which gives you an average of 1 event every 700,000 years, and from that you derive an annual probability. The math works. It just rests on assumptions that may not hold. The first assumption is that the system is statistically uniform, that each year carries roughly the same chance of an eruption as any other. This is what statisticians call a Poisson process, and it is a reasonable starting point when you know almost nothing about the underlying physics. But for Yellowstone, we know quite a lot about the underlying physics, and what we know suggests strongly that the annual probability is not uniform. The chamber today is in a quiet phase, solid rock, low melt fraction, no volatile saturation, no signs of the pressure buildup that would precede an eruption. So the actual annual probability for a year like this one, with conditions like the conditions we currently observe, is almost certainly lower than the long-term average. How much lower, we cannot say with precision. But the official figure of 1 in 700,000 is, as the USGS has noted explicitly more than once, an overestimate for the short term. The real probability for any given year in the foreseeable future is probably closer to zero than the average suggests. The second assumption is that 3 data points are enough to constitute an average. We talked about this earlier in a different context, and the same problem applies here. With 3 eruptions and 2 intervals between them, the statistical foundation for any rate calculation is shaky. The intervals were 800,000 years and 670,000 years, which means the system varies by more than 15% across just 2 observed cycles. With more cycles, that variance might grow. It might shrink. We do not know. The number we have is the best we can do with the data available, which is the same as saying it is approximate, provisional, subject to revision when better information comes along. The third assumption is the most subtle and possibly the most important. It is the assumption that the system will continue to behave the way it has behaved. There is some evidence, as we discussed in connection with Mesa Falls, that the Yellowstone hotspot may be approaching the late stages of its active life. The geochemistry of the most recent eruptions resembles the geochemistry of the final eruptions at Heiser, the older caldera complex to the west that the hotspot used to occupy. If that interpretation is correct, then the probability of future eruptions at Yellowstone is not merely small. It may be declining. The system may be winding down rather than continuing in steady state. There may be 1 or 2 more events ahead of it, or there may be none at all. The hotspot will keep moving, the heat will eventually shift northeast, and what we currently call Yellowstone will become as quiet over the coming millions of years as Heiser is quiet today. Now, none of this means we should ignore the possibility of an eruption. Tail risks are real. The world is full of low-probability events that, when they actually happen, produce catastrophic consequences. Pandemic preparedness, asteroid detection, nuclear safeguards, climate adaptation – all of these are areas where modern societies invest substantial resources to mitigate risks that have very low annual probability and very high potential impact. Yellowstone falls into the same general category. The probability is small. The consequences, if it ever did happen, would be enormous. So we monitor it, we study it, we plan for it in the limited ways that planning for an event of this scale is even possible. But we do not, if we are being honest with ourselves, treat it as imminent. There is no version of the available evidence that supports treating it as imminent. The eruption is a future possibility, very far in the distance, with a probability that gets smaller the more carefully you look at the actual physics of the chamber. The cultural conversation around Yellowstone tends to obscure this. Every few years, a video circulates online claiming that recent earthquake activity or recent ground deformation or some new piece of research indicates that the supervolcano is about to erupt. The claims are almost always wrong. They are based on misreadings of data, on selective quoting of scientific papers, on the deep human attraction to apocalyptic narratives. They get attention because they are dramatic, and the actual scientific consensus, which is essentially that Yellowstone is in a quiet phase and likely to remain so for the foreseeable future, is not dramatic enough to compete in the marketplace of online attention. The result is a chronic mismatch between what the science says and what most people believe about Yellowstone, and the mismatch tends to drift over time in the direction of unwarranted alarm. This is worth pushing back on, gently, not because supervolcanoes are unimportant, but because the genuine hazards at Yellowstone are different from the ones people worry about. There are real dangers in the park. They are not the dangers you have probably heard about. They are smaller in scale, more frequent, and far more likely to actually affect a person walking through the park on any given afternoon. The Yellowstone Volcano Observatory tracks them carefully, and they have a particular event from the summer of 2024 that they like to point to when they are explaining to visitors what to actually be concerned about. It happened on a Tuesday morning in July in a part of the park called Biscuit Basin, and it changed how everyone in the park's hazards office thinks about the immediate future of Yellowstone. On the morning of July 23, 2024, a group of perhaps 100 tourists was standing on the boardwalk at Biscuit Basin, a small thermal area in the western part of Yellowstone National Park, about 3 kilometers north of Old Faithful. It was a Tuesday. The weather was warm, the sky was clear, and the tourists were doing what tourists do at Biscuit Basin on a summer morning. They were taking photographs of the hot pools, leaning on the wooden railings, listening to the soft bubbling of water that has been heated underground and is reaching the surface for the first time. A particular pool called Black Diamond, smaller and quieter than some of its more dramatic neighbours, was sending up the gentle plumes of steam that it had been sending up more or less continuously for as long as anyone in the park service had been keeping records. At 10:19 in the morning, Black Diamond exploded. There was no warning. There almost never is. The pool, which had been calmly venting steam a moment earlier, suddenly erupted in a column of boiling water and shattered rock that rose more than 10 meters into the air. Fragments of stone, some of them the size of human heads, were thrown outward in all directions. The boardwalk where the tourists had been standing seconds before was shredded, its planks splintered and scattered, the metal handrails twisted and bent. The pool itself was destroyed, replaced by a steaming crater, and in what can only be called extraordinary luck, no one was killed. A few people were injured by flying debris, several were drenched in scalding water. But the timing of the event happened to be just slightly off from the moment of maximum visitor density at that particular spot, and the position of those tourists who were closest happened to be just barely far enough away to put them outside the worst of the blast radius. By any reasonable accounting of how it could have unfolded, the Biscuit Basin event of July 2024 was a near miss of considerable magnitude. People who would have died if they had been standing 2 meters closer were still alive when the dust settled. This is the hazard at Yellowstone that almost nobody talks about, and it is the hazard that the Yellowstone Volcano Observatory will tell you about at length if you ask them what actually keeps them up at night. It is not the supereruption, it is the hydrothermal explosion, and the difference between the two, in terms of how often they happen and how directly they affect people who visit the park, is enormous. To understand what happened at Biscuit Basin, you have to understand how the hydrothermal system at Yellowstone actually works. We touched on this earlier in passing, but it is worth spending a few minutes on the mechanism in detail, because the mechanism is what makes these events both inevitable and nearly impossible to predict in advance. The plumbing system that produces the geysers and hot springs is not a simple network of clean pipes. It is a vast tangle of fractures and channels in the broken rock above the magma chamber, full of water at all different temperatures and pressures, with mineral deposits constantly forming and dissolving, sealing some passages and opening others. Water heated by the deeper magma rises through this network. As it rises, it stays liquid because the pressure of the water column above it keeps it from boiling, even though its temperature is well above what would be the boiling point at surface conditions. In some places, deep below the geyser basins, water exists at temperatures of more than 200 degrees Celsius, in liquid form, held that way by pressure alone. This is an unstable arrangement. It does not seem unstable because it persists for years and decades and centuries without changing, which is why we feel comfortable building boardwalks above it and inviting people to admire the hot springs. But the equilibrium depends on the pressure above the superheated water remaining steady. If something disturbs that pressure, a sudden drop, a small earthquake, the collapse of a mineral seal, the slow erosion of a confining layer, the superheated water does what physics says it must do. It flashes instantly into steam, Steam occupies a volume more than 1,600 times larger than the same mass of liquid water. The transition is essentially instantaneous, and the energy released by that transition has to go somewhere, and the place it goes is upward, through whatever is in its way, including the rock and soil and boardwalk and tourists. A hydrothermal explosion is not a magmatic event. No fresh magma reaches the surface. No new rock comes up from the deep system. What you have instead is a sudden flashing of pre-existing water into pre-existing steam, followed by the violent ejection of whatever solid material happened to be sitting on top of that water. The explosions can be small, as Black Diamond was, throwing rocks for tens of meters and creating craters a few meters across. Or they can be enormous. The largest hydrothermal explosion crater anywhere in Yellowstone is at a place called Mary Bay, on the northern shore of Yellowstone Lake. Mary Bay is about 2.5 kilometers across. It was formed in a single event, somewhere around 14,000 years ago, when an earthquake almost certainly disturbed the pressure on a vast underground reservoir of superheated water, and the entire system flashed into steam at once. The crater is so large that you cannot easily see its shape from the ground. You have to look at it from the air, or on a map, to understand what happened there. A circle of disturbed earth and lake water, 2.5 kilometers wide, blasted into existence in a matter of seconds. There are at least 20 similar craters known in the Yellowstone region, formed at various points over the past 14,000 years. Some are now small lakes: Indian Pond, Turbid Lake, the small basin at Pocket Basin. Others have been worn down by time and are visible only as broad circular depressions in the landscape. The Yellowstone Volcano Observatory keeps a running catalogue of them and continues to find new ones as more careful mapping is done. The pattern, when you look at all of them together, is that hydrothermal explosions of significant size happen somewhere in the park every few centuries on average. The smaller ones, like Black Diamond, happen far more often. The Yellowstone hazard staff estimate that hydrothermal explosions large enough to be locally dangerous occur at a rate of roughly 1 every 2 years, though most of them happen in remote backcountry areas where no one is present to witness them or to be killed by them. This is, by an enormous margin, the most likely volcanic hazard at Yellowstone. The probability that some kind of hydrothermal explosion will occur somewhere in the park during the next decade is essentially 1. It is not a matter of if, it is a matter of where and how big, and whether anyone happens to be standing nearby when it goes off. The Biscuit Basin event of 2024 was a reminder, quite literally, of this fact. The boardwalk that exploded that morning had been considered a safe place to stand for as long as anyone could remember. There was nothing in the historical record, nothing in the monitoring data, nothing in the visible behavior of Black Diamond Pool that would have warned anyone the eruption was coming. It just came. There are other hazards too, and they are also worth a moment. Earthquakes are common in the region. Yellowstone sits at the intersection of several active fault systems, and the largest historical earthquake in the central Rocky Mountains, a magnitude 7.5 event in 1959, struck near Hebgen Lake, just outside the park boundary. That earthquake killed 28 people, most of them buried by a massive landslide it triggered. Earthquakes of magnitude 6 or 7 are expected to recur in the Yellowstone region every century or two, and any of them could produce significant local damage. They could also, in principle, trigger hydrothermal explosions or destabilize parts of the magmatic system, although the historical record shows that even substantial earthquakes have generally not produced major volcanic responses at Yellowstone. There are smaller volcanic events that are also possible. A lava flow inside the caldera, similar to the rhyolite flows that built much of the present landscape between 160,000 and 70,000 years ago, would be a much more local affair than a supereruption, confined to the park slow-moving, damaging mostly to property and habitat rather than to populations far away. Such an event would probably be detectable in advance, because the build-up to a magmatic eruption typically produces measurable seismic and deformation signals over weeks or months. The Yellowstone Volcano Observatory would have time to issue warnings, evacuate the affected area, and prepare emergency responses. The damage would be substantial but largely manageable on the scale of an active volcano elsewhere in the world rather than a continental catastrophe. So if you put all of this together, what you get is a hazard hierarchy that looks almost nothing like the one most people carry in their heads. The most likely event, by an enormous margin, is a hydrothermal explosion somewhere in the park within the next few years, probably small, probably in an area where it does no harm, but possibly large and possibly in a tourist area where the consequences could be serious. The second most likely event is a substantial earthquake within the next century or so. Far less likely than either of those, but still within the realm of plausible outcomes over the next few thousand years, is a smaller magmatic eruption inside the caldera. Vastly less likely than any of these is a full supereruption of the kind that built the modern landscape. The supereruption is the one everyone worries about. It is the one that gets the films and the documentaries and the late-night conspiracy videos. It is also the least likely thing to happen at Yellowstone in the next several thousand years. The actual everyday work of monitoring this system, of watching for the signs of any of these events and being prepared to respond when they come, is done by a relatively small group of people scattered across 9 institutions, working with an enormous and constantly evolving array of instruments. They are the reason we know what we know, and they are the reason that, for the moment at least, we can say with reasonable confidence what the system is doing and what it is not. The Yellowstone Volcano Observatory is not a single building. There is no central headquarters with a sign on the door, no control room with banks of glowing screens, no team of scientists sitting around a table waiting for the supervolcano to do something interesting. The observatory is a consortium, an arrangement of 9 separate institutions that share data and coordinate research and produce a single set of public communications about what is happening underneath one of the most carefully watched pieces of land on the planet. The United States Geological Survey is the lead agency. The University of Utah operates most of the seismic instruments. The National Park Service maintains the surface infrastructure. Several other universities and state geological surveys handle specific monitoring functions or contribute particular expertise. The whole arrangement was formalized in 2001 after several decades of less organized cooperation, and it has been refining itself ever since. What the observatory actually does in any given week is collect and interpret an enormous quantity of data from sensors distributed across and beneath the entire Yellowstone region. There are something like 30 seismometers in the network, ranging from small portable units to deeply buried instruments designed to detect the smallest possible vibrations in the rock. There are dozens of continuous GPS stations, each one capable of measuring the position of a point on the ground to within a few millimeters, monitoring the very slow rise and fall of the caldera floor over time. There is a satellite-based system called INSAR, short for Interferometric Synthetic Aperture Radar, which uses radar pulses from orbit to map ground deformation across the entire region with even greater precision than the GPS network alone could provide. There are gas sensors at multiple thermal areas, measuring the chemistry of what comes out of the soil and the springs, watching for changes in the carbon dioxide flux or the hydrogen sulfide concentration that might indicate something shifting at depth. There are temperature sensors in the geyser basins, infrasound microphones to detect explosions, stream gauges to track the underground water table. The whole system operates 24 hours a day, every day, and the data flows continuously into the analysis centers in Salt Lake City and elsewhere. where it is examined and processed and interpreted in something approaching real time. The picture that emerges from all of this monitoring is, on most days, almost boring. There is always something happening. Yellowstone is an active geological region. In a typical year, the seismic network records somewhere between 1,500 and 2,500 small earthquakes, the great majority of them too small to be felt by anyone, occurring at depths from less than a kilometre down to as much as 20 kilometres. About half of those earthquakes happen in clusters that geologists call swarms, sequences of small events occurring close together in space and time, usually associated with the movement of hot fluids through fractures in the rock rather than with any movement of magma. The largest earthquakes in any given year are usually in the magnitude 2 to 3 range, which is large enough to be felt by people standing nearby, but not large enough to cause damage. Felt earthquakes occur perhaps 5 to 10 times annually. None of this is unusual. None of it is alarming. It is simply what an active hydrothermal and tectonic system does when it is going about its ordinary business. The ground itself is also moving slowly in patterns that the GPS and INSAR networks have been tracking carefully for decades. Over the past several years, since approximately 2015, the floor of the Yellowstone caldera has been gradually subsiding at a rate of about 2 to 3 centimeters per year. This is the kind of movement that would be impossible to detect without modern instruments. You could not feel it, you could not see it, you could not measure it with anything less precise than satellite radar or millimeter-grade GPS. But it is real, and it is consistent, and it has been going on for nearly a decade. The interpretation, as far as the science can currently tell, is that this gradual subsidence reflects the slow cooling and contraction of the magma system below, a sign that the chamber is not gaining heat or pressure, but losing them. There are seasonal interruptions to this pattern, periods each summer when the subsidence pauses or briefly reverses, and these are explained by the seasonal cycle of snowmelt and groundwater recharge, which adds weight to the system and changes how the surface deforms in response to what is happening underneath. But the long-term trend is downward. The caldera is sinking, slowly. Mixed in with this gradual subsidence are occasional episodes of more rapid uplift in localized areas. The most recent of these began in July of 2025, in a region along the northern rim of the caldera, where ground deformation accelerated to several centimeters of upward movement over the course of a few months. This was accompanied by an increase in seismicity, including a notable earthquake swarm in November of that year, occurring directly above the area of greatest uplift. By early 2026, the uplift had paused. The seismicity had returned to background levels. Whatever had caused the temporary acceleration appeared to have run its course, and the longer-term pattern of slow caldera subsidence resumed. This kind of localized uplift is not rare at Yellowstone. There was a similar episode between 1996 and 2004, and another, even more dramatic one between 2004 and 2008, when a portion of the caldera floor rose at a rate of nearly 7 centimeters per year before slowing and reversing. These events come and go. They have so far always come and gone without producing anything more dramatic than the deformation itself. But the staff of the observatory watch them carefully, and they watch them carefully because the build-up to a real magmatic eruption, if one ever did occur at Yellowstone, would almost certainly involve patterns of deformation and seismicity far more pronounced than anything observed in modern times. The current consensus is that any future eruption would be preceded by weeks, months, or more likely years of accelerating signals. deep earthquake swarms migrating toward the surface, ground deformation rates an order of magnitude greater than what we currently see, sustained increases in gas emissions, changes in the chemistry of the hydrothermal system, behavioral shifts in the geyser basins. The signs would be, by all reasonable expectations, unmistakable. They would not appear overnight. They would build, gradually but steadily, over a long enough period that the population of the region could be warned and, if necessary, evacuated. None of those signs is currently present. The system is, by every measure that matters, in a quiet phase. The hydrothermal events are different, and this is where the monitoring is genuinely incomplete. A hydrothermal explosion of the kind that destroyed the Black Diamond Pool Boardwalk in 2024 cannot be predicted in any meaningful sense. The system that produces such an event is too complex, too dependent on small-scale fluctuations in pressure and temperature deep in fractured rock for any monitoring network we have to give useful warning. The observatory deploys infrasound and seismic sensors in the most heavily visited thermal areas, and these instruments will record an event the moment it begins, which is helpful for understanding what happened, but not very helpful for warning anyone in advance. After the 2024 event, the observatory installed a new webcam at Biscuit Basin and added additional monitoring equipment to the area, and they have plans to expand similar coverage to other high-traffic thermal areas. But the hard truth is that hydrothermal explosions happen suddenly with little or no warning, and the only real protection is to limit the time and location of human exposure. Boardwalks help. Staying on the trails helps. The protection is statistical, not absolute. People who walk through the geyser basins are not in serious danger on any given day, but the possibility of an unlucky encounter with a sudden hydrothermal event is, mathematically, never zero. This is the work the observatory does. They watch. They process the data. They publish a monthly update, which goes out on the first of each month and summarizes the previous month's activity in plain language for anyone who wants to read it. The updates are remarkable for their evenness of tone, their refusal to sensationalize, their willingness to say plainly when nothing of consequence has happened. Most months, that is what they say. Most months, the most interesting thing in the report is a particular geyser that erupted more frequently than usual, or a small earthquake swarm in one corner of the park, or an instrument that needed replacement. The reports are read by a small audience of professional geologists, by a slightly larger audience of dedicated park enthusiasts, and almost ignored by the wider public, except in the rare cases when something happens that makes the news, at which point the public attention spikes briefly, and the observatory finds itself trying to explain, in interviews and press releases, that whatever happened is not the precursor to the supereruption that everyone keeps asking about. There is a quiet dignity in this work. The scientists involved have spent their entire careers studying a system that, in human terms, will probably never do anything dramatic. They monitor it because monitoring is the right thing to do. They publish their results because the public has a right to know. They correct misinformation when they encounter it, often patiently, often without much success against the machinery of online speculation. And they go home at the end of the day to lives that look very much like the lives of anyone else, knowing that the chamber under Wyoming will, by every measure they can take, still be there in the morning, still mostly solid, still slowly cooling, still doing what it has been doing for the last 70,000 years, which is essentially nothing. The question of what comes next, then, for Yellowstone, for the Hotspot, for the long-term geological future of this part of North America, is a question that operates on timescales the observatory cannot really speak to. The instruments measure what is happening now. The geological record tells us what happened before. To think about what might happen in the next 100,000 or million years requires a different kind of imagination, a willingness to step outside the immediate present and consider the slow rhythms of a planet that has been doing this for billions of years and will continue doing it long after the question of human civilization has ceased to be relevant. 100,000 years from now, the surface of the Earth will be unrecognizable in some places and almost identical in others. The continents will sit in roughly the same positions they occupy today, because plate tectonics moves at a pace that even 100 millennia cannot meaningfully alter. The Atlantic Ocean will be perhaps 2 kilometers wider. The Himalayas will be a few centimeters taller. The Mississippi River will have carved itself into a slightly different channel through the lowlands of Louisiana, finding new paths to the Gulf as the old ones silt up and abandon themselves. Most of these changes will be invisible at any human scale. You could walk from one century to another across the long arc of those 100,000 years and notice nothing. But certain things will have moved significantly. The North American plate, which is currently sliding southwestward over the stationary Yellowstone hotspot at a rate of about 2.5 centimeters per year, will have carried its current position by roughly 2.5 kilometers. That is not very far in human terms, a comfortable walk on a mild afternoon. In geological terms, however, it is enough to begin a transition. The hotspot, which today sits beneath northwestern Wyoming, will then sit beneath what is currently a slightly different patch of ground, a few kilometers to the northeast of where the modern caldera lies. The shift will be too small to notice as a single event, but over hundreds of thousands of years, those small movements will add up to something profound. This is how the Yellowstone hotspot has worked for the entire 16 million years of its existence. It does not move, the continent does. And as the continent slides, the hotspot occupies a sequence of different addresses, building each one up into a region of intense volcanic activity for a period of perhaps 2 or 3 million years before the slow westward drift of the overlying plate carries it elsewhere, and the old volcanic field begins its long decline into silence. We can read this history backward along the trail the hotspot has left across what is now Idaho, and we can use the same principle to look forward, to project where the hotspot will be sitting in the deep future and what it might be doing there. In maybe 1 million years, perhaps a little more, the active center of volcanism will have shifted from Wyoming into southwestern Montana. A new caldera complex may begin to form there, possibly with eruptions on a scale we would recognize from the Yellowstone history we have just walked through. The current Yellowstone caldera will, by then, be in a state similar to what we see today at the older calderas along the Snake River Plain, quiet, eroded, slowly filling with sediment, no longer producing major eruptions. The hot springs will gradually cool as the heat source moves away. Old Faithful, if it still exists in any recognizable form, will become less faithful. The hydrothermal features that draw 3 million visitors a year today will, over the course of a few 100,000 years, lose their energy and fade into ordinary cold water springs. The bison and elk and wolves will still be there, presumably in some form, doing what bison and elk and wolves have always done. But the geyser basins will be gone. Further out, 5 million years, 10 million years, 15 million, the hotspot will continue its slow march northeastward across what is now the United States and into what is now Canada. Each successive caldera complex will rise and then quiet, leaving behind a chain of buried craters that some future geologist, if such a thing exists by then, may study with the same fascination that current geologists bring to the Snake River Plain. The trail will lengthen, the pattern will continue. Eventually, perhaps 50 or 100 million years from now, the hotspot may reach the edge of the North American plate at one of its boundaries, and at that point, the entire system will become something different, incorporated into the spreading or subducting margin, transformed in ways that are difficult to predict from the present configuration. Or it may persist, quietly and stubbornly, beneath whatever piece of continent happens to be sitting above it, for as long as the deep mantle continues to deliver hot rock from the boundary with the core. That is not the kind of question we can answer from where we are standing. There is an open question about whether Yellowstone, as a volcanic system, may have already entered its final phase. We have touched on this once or twice already, but it is worth returning to here in more detail because it has consequences for how we should think about the entire question of future eruptions at this site. The Yellowstone hotspot, before it sat under Wyoming, sat under a region of eastern Idaho called the Geyser Volcanic Field. The Geyser sequence consisted of 4 major caldera-forming eruptions over a period of about 2 million years, beginning around 6.5 million years ago, and ending with a final massive event called the Kilgore Tuff, which erupted around 4.5 million years ago. The Kilgore eruption produced something like 1,800 cubic kilometers of magma, which makes it larger than any of the 3 Yellowstone eruptions, and it represented the last major activity of the Geyser field. After Kilgore, Geyser went quiet. It has not erupted since. The chamber cooled, the magma solidified, and what was once a region of cataclysmic volcanism became, as it remains today, a quiet agricultural valley. This pattern, 4 caldera-forming eruptions, decreasing in some respects over time, ending with a final large event followed by the cessation of activity, is the only complete eruptive cycle we have to compare Yellowstone against. And there is geochemical evidence that Yellowstone may be following a similar trajectory. The isotope signatures in the most recent volcanic rocks at Yellowstone, the post-caldera lava flows that have erupted since the Lava Creek event, show certain characteristics that resemble what we see in the late Geyser sequence. Specifically, the magmas appear to be increasingly dependent on the remelting of older crustal material rather than on the addition of fresh material from below. The system may be running out of usable fuel. The crust above the plume may have been substantially depleted by the previous 3 caldera-forming events, and what is left may not be sufficient to produce another major eruption on the same scale. This is one interpretation. It is not the only one, and the evidence is sufficiently ambiguous that other interpretations are equally defensible. But if it is correct, it would mean that Yellowstone has, at most, one more major eruptive event ahead of it, and possibly none at all. The hotspot itself is still active. The plume is still rising. But the part of the crust currently sitting above the plume may have already been used up in the way that matters, leaving only the slow geothermal expression of residual heat, the geysers, the hot springs, the hydrothermal explosions, without the capacity to produce another super-eruption of the kind that built the modern caldera. Whether or not Yellowstone has one more event ahead of it, the deeper picture is the same. Supervolcanoes do not run forever. Each one occupies its window in geological time, builds its calderas, deposits its tuffs, and then quiets down. The hotspot continues. The plate continues to move. The location of intense activity shifts. New volcanic fields are born somewhere else, and the cycle begins again in a slightly different place, with a slightly different chemistry and a slightly different history. The planet has been doing this for billions of years. It will keep doing it for as long as the deep interior continues to lose heat into space, which is to say, for as long as the planet itself remains a coherent thing. It is worth pausing briefly to remember that Yellowstone is not the only supervolcano on Earth. There are perhaps a dozen others scattered across the globe that have produced eruptions in the same magnitude class within the geologically recent past. Toba in Sumatra erupted about 74,000 years ago and is still considered an active system. Long Valley in eastern California produced the Bishop Tuff 760,000 years ago and remains volcanically alive, with periodic episodes of unrest that bring it briefly into the news. Taupo, on New Zealand's North Island, erupted catastrophically about 26,000 years ago and again on a smaller scale, in the year 232 of the Common Era, the most recent super-eruption class event on Earth. Campi Flegrei, the great caldera that lies beneath the western suburbs of Naples, has been showing signs of unrest for several decades, with substantial ground deformation and elevated seismicity that has prompted concern among the volcanologists who study it most closely. None of these systems is currently expected to produce a super-eruption in any human-relevant timeframe, but they are reminders that Yellowstone is not unique. The mechanism that produced the Lava Creek event is operating in some form in many places around the planet, and the eventual occurrence of another super-eruption somewhere on Earth, sometime in the next few 100,000 years, is essentially a statistical certainty. Where it will happen and when, we cannot say. That it will happen, eventually, is built into how the planet works. So when we ask what comes next for Yellowstone, the honest answer is that we do not know with any precision, but we can sketch the general shape of the future fairly confidently. The chamber under Old Faithful will remain quiet for a long time, probably tens of thousands of years at minimum, possibly much longer, possibly forever. The hydrothermal system will continue to do what it does: boil, vent, occasionally explode without warning, kill the rare unlucky tourist who happens to be standing in the wrong place at the wrong time. Earthquakes will continue in their slow rhythm of swarms and clusters. The caldera floor will continue to rise and fall by small amounts each year, a few centimeters in either direction, as the system slowly equilibrates with itself. Eventually, perhaps in 100,000 years or perhaps in 1,000,000, the hotspot's center of activity will begin to shift northeastward, and Yellowstone will begin its long transition into the kind of quiet that Heiser enjoys today. New volcanism will emerge somewhere else. The cycle will continue. And we, the species that has been watching all of this for a few hundred years and understanding it for a few decades, will be doing whatever we will be doing by then, in whatever forms we will then take. It is impossible to know. The future of human civilization is contingent on so many factors that any extrapolation across 100,000 years is essentially fiction. What we can say is that the geological story will continue regardless. The plate will keep sliding, the plume will keep rising, the chambers will keep filling and emptying, somewhere on the planet, on schedules that have nothing to do with us. And that is, in its own quiet way, both humbling and clarifying. The recognition that the system we have spent 12 chapters trying to understand is part of a much larger system, one that does not require our attention to function and will continue functioning whether we are here to observe it or not. We have spent a long time now in the company of one mountain, one chamber of magma, one corner of one continent. We started at the surface with the geyser that erupts on schedule and the tourists who gather to watch it. We followed the heat downward, through the crust, through the layered chambers of partially molten rock, into the deep mantle plume that rises from the boundary with the core. We watched the system erupt 3 times across 2 million years, and we saw what it left behind. We considered the physics of how a magma chamber crosses the threshold from quiet to catastrophic, and we walked through what would happen, in modern terms, if it ever crossed that threshold again. We measured the probability, we ranked the actual hazards. We met the small group of scientists who watched the system on a continuous basis, doing patient work that almost no one will ever notice, on behalf of a civilization that mostly does not understand what they are protecting it from. And we looked briefly at the deep future, at the slow march of the hotspot toward whatever comes next. What stays with me when I think about all of this together is not the catastrophe. It is the recovery. 3 times, the chamber under what is now Yellowstone has emptied itself onto the landscape with a violence that is almost impossible to imagine. 3 times, the continent has been buried under meters of ash. 3 times, the climate of the entire planet has shifted in ways that produced famines and migrations, and the deaths of more living things than anyone could count. And 3 times, the world has come back, not the same world. The plants that survived were different from the plants that died. The animals that recolonized the ash plains were different from the animals that perished. The forests that grew over the lava creek deposits were not the same forests that had stood there before the eruption. But they were forests. Life returned, not because anything chose to bring it back, not because some intervention ensured the recovery, but because life is what happens on a planet like this one, given enough time and enough water and enough sunlight. Recovery is the default. Catastrophe is the interruption. This is the piece of the story I would like you to hold on to, more than any of the rest of it. The magma chamber and the eruption mechanics and the probability calculations are interesting in their own right and worth knowing for their own sake. But the deeper lesson, the one that emerges only when you put all the pieces together, is that the planet has been doing this for a very long time. Eruptions of this scale have happened, by the most conservative estimates, more than 600 times in the geological history of the Earth. The vast majority of them happened before any creature was alive to witness them. A handful happened within the lifespan of our species, on the order of a few thousand human generations. We are, in geological terms, living through what amounts to a brief lull between events that we know, with almost mathematical certainty, will eventually happen again. Somewhere. Not necessarily here, not necessarily soon, but eventually. And what the geological record shows, with a clarity that is almost unsettling once you really absorb it, is that none of those previous events ended the world. None of them stopped life. None of them meant the planet stopped being a place where complex things could grow and reproduce and look up at the sky and wonder where they came from. The world has been, in this sense, indestructible. Not because nothing can hurt it, but because it has been hurt many times, and it has always come back, and there is no obvious reason to think the pattern will not continue. I want to put that another way, because it is the thing that took me longest to really understand, and I think it is worth stating as plainly as I can. The planet does not need us. It will continue without us, as it continued before us. Over the long arc of geological time, our species is a brief thing, a small thing, a recently arrived thing, whose departure, whenever it eventually comes, will leave the planet largely unchanged. This sounds, when you say it out loud, like a depressing thought. It is not. It is, when you sit with it, an enormously freeing thought, because it means that the thing we are part of, this slow, vast, patient process of a planet doing what planets do, is bigger than we are, and older than we are, and will outlast us by an unimaginable margin. We do not have to save it. We do not have to preserve it forever. Our job, if we have one at all, is simply to live within it for the brief time we are here, and to understand what it is, and to be grateful that we got to see any of it at all. The chamber under Yellowstone is sleeping. It has been sleeping for 631,000 years, which is longer than our species has been a species. Whether it wakes up tomorrow, or in 100,000 years, or never, the answer matters very little to the chamber itself. The chamber is what it is. The plume that feeds it will continue to rise from the deep mantle, slowly, patiently, on a schedule measured in millions of years. The plate above it will continue to slide, slowly, patiently, on the same schedule. And somewhere, sometime, the system will do what systems like this one do, and the world will absorb the event and recover and continue the way it has continued before. If you are listening to this in the dark, late at night, perhaps with the lights off, perhaps with someone sleeping beside you, you are part of that long continuation. You exist on a planet that has been making and unmaking itself for 4.5 billion years, and you are conscious of it briefly in this small moment, in this small slice of the present. The geyser will erupt again tomorrow morning. The bison will graze in the meadows. The hot springs will steam in the cold air, and the boardwalks will sit above the magma chamber. And 3 million people a year will walk across them and look down at the water without ever knowing what is underneath. The system will go on. It always has. There is, in all of this, a quietness that I find I cannot quite describe. The slow rhythm of a planet that is doing what it has always done. The chambers that fill and empty over hundreds of thousands of years. The plumes that rise from the boundary with the core, lifting heat outward century by century, millennium by millennium. The hot springs that have been bubbling for longer than recorded history and will go on bubbling long after the last human voice has fallen silent. None of it is for us. None of it depends on us. None of it requires that we be here to observe it. And yet, for a brief moment, we are here, and we can observe it. And that is, I think, the closest thing to a gift that the universe has to offer. The chamber sleeps. The plume rises. The continent slides slowly to the southwest, and the hotspot stays where it is. And somewhere ahead of us, in the long arc of time, there will be another eruption, and another recovery, and another long silence. We will not see it. The people we love will not see it. The civilizations we have built, with their cities and their books and their accumulated wisdom, will likely not see it either. But the world we are part of will see it, will absorb it, and will go on. The planet does not forget, but it does not remember either. It just continues. And that is, in the end, enough. If you find yourself awake somewhere in the middle of the night in the weeks and months ahead, and your mind drifts to the question of what is coming, of what waits beneath the surface of the world, I hope some of what we have walked through together will come back to you. Not as worry, not as dread, but as a kind of perspective. The thing you are afraid of has happened many times before. The thing you are afraid of has been survived many times before. The world has been here longer than we can imagine, and it will be here longer than we can imagine after we are gone. And the chamber under Old Faithful will sleep through most of it, the way it has slept through most of everything. Rest now. The planet is patient. The geyser will erupt at sunrise. The hot springs will go on steaming. Somewhere under Wyoming, in a place that no one will ever see, the magma waits, the way it has waited for 630,000 years. There is no hurry. There never was. Good night.